Hi everyone and welcome to today's session. Today is one of my most important sessions because I'm going to talk about my future research plan. So this is learning fast and slow, and it is basically a way for an agent to learn from its own experiences by having two ways of learning. One is a neural network to predict the next action given the start state and the goal state, and the other will be a memory-based network in order to do planning into the future, in order to use past experiences to ground its current action. So this is a new idea that I thought of like at NeurIPS last year. And I think this idea is very, very useful and can lead to a lot of different things that could make fast and adaptable agents. Okay, there could be plenty of use cases. One of them is perhaps self-driving cars and a lot more others the moment this idea is developed. And so today we are going to talk about the plans I have in order to develop them. And also, this is not just a one-way session. I hope to have some discussion because I don't have the full answers to everything. So before we begin, let me just go through the baseline model. So I just presented this last month at Macau. And this basically talks about the fast and slow method. So as you can see over here on the left side, we have the fast model, which is the neural network. And this model basically just predicts an action. So like current state, like you are in this part of the maze and you want to reach this door over here, my first action could be I go right. I mean, I could go right or go down. Yeah, but it's basically it's a very course guide. It's like a compass in the middle of the woods. You're trying to find your direction. You just predict your first action. This may not be accurate, okay, because you don't do the look ahead planning. The look ahead planning happens here when you can do multiple branches of planning retrieval using memory as a baseline. So like if you have experienced like a path over here before, like for example, this purple path here, okay, you might retrieve this path in this branch. And then the first action will then become the action that's output here, like the action down and this action right. So if we could get something here, okay, if we could get some action from our memory, which means that we already know how to solve this problem before, we can override our fast neural network, okay, and just do the down action. So this right side is what I call a slow memory retrieval. And it is actually the most accurate way of planning because we ground it on our past experiences. Okay, on the left here is just a very crude way of giving a fast decision. Like this is more like intuition. Okay? So this has been quite successful in changing environments, and it beats like more than 30%. Like in terms of the 10 by 10 grid world, it beats PPO hands down, because in this dynamic grid world, the start state and end state changes every single episode. So PPO takes a while to learn, while this method, because it's goal directed and it uses both memory and the non-memory part, it beats PPO quite a lot, a significant margin, about 30% in 10 by 10 grid world. I think it wins by about also a similar percentage in a 40 by 40 grid world. So how does this work? Okay, this is the traditional the traditional reinforcement learning. And in reinforcement learning, basically we have a current state, we have a current action, all right? We go through the environment like we move right in the grid world. The environment will tell us where we are next. Okay, we go to one cell to the right. Okay, and then in traditional reinforcement learning, there's this thing called reward. And this reward, where does it come from? It comes from the environment. Okay, it means the environment needs to tell us, hey, this is a good action, this is a bad action. Okay, obviously, if you think about in real life, whether you get a reward or not is probably not by the environment. It's actually by yourself, internal. It's actually what people call like intrinsic motivation, where you get rewarded by your own systems inside. Like, oh, you eat an ice cream, you feel very happy. Okay, the environment outside doesn't really care whether you eat an ice cream or not. There's no external reward. Okay, but in this case, reinforcement learning problems have this external reward. All right, and okay, the main thing about this external reward signal in reinforcement learning is that it's very slow to learn. Okay, so I've experimented with architectures like AlphaZero. Okay, and basically, while they are great, if you can use the same environment millions of times, all right, they will self-improve. But in real life, you know, how many times is the environment going to be exactly the same, right? So if you take a look at this graph, this grid here, you have the person here, and you have the door here yourself go to. And let's say we give an external reward of 1 to the door. All right, you can also make it an internal reward. Okay, it's both internal and external rewards both also have the same argument against it. Okay, it takes very long to calibrate yourself. Okay, if let's say this is an external reward, you need to back propagate this reward back and say that, oh, the value of this second cell is 0.9, 0.8. You can use some decay method. This is the Bellman update in order to update your cells. And maybe over here, this value will be 0.1. And then this value is 0 because like we have this path here and then like the value here is 0.2 and so on. So at each step, what we can do is we can just choose the state that gives you the highest reward or the highest value. In this case, go right. So you can back propagate like that. Okay, the problem is that you need to back propagate for all the states in a row, one by one. And the moment this door changes, let's say the door goes here. Can you see that we need to relearn all your values again because you need to now take into account that this is the end state and you need to back propagate your values like that. Okay, so in a static environment, reinforcement learning techniques have no problem. All right, they will learn. Okay, in fact, they will learn optimally because you keep improving using this one-step Bellman update. Okay. However, if the environment changes, you need to keep learning a different value function. Yeah, I mean, people have tried to say that, oh, I can do a goal-directed value function where you have a state and goal like that. Yep. Or yeah. So basically for different goal states, you have different value functions and so on. Yes, I mean, you could try to learn something like that. But actually the main thing that we really need to do is to just predict an action. Okay, I don't really care about like whether the value is high or low, you know, as long as you can get a general direction to your goal, that's good enough. So my research has led me to conclude that actually value functions may not be needed. All right. So this applies to external reward signals or external value functions. If internal reward signals are correlated to the environment, then it also applies for the internal value signals as well. Okay, so Kyrian asks, in a self-driven car situation, the goal would be the final destination. Yes, you can think of that as the goal. So later on, I will talk about more on goals because I think there are different kinds of goals you can align to. And this is something that we need to think about as well. But definitely, if you talk about a self-driving car, you want to get from point A to point B, your point B could be the goal. So this is the two neural networks that I was talking about earlier. So the main thing is this is more like gut feel intuition. It just gives you the action. So you can see we don't even have the value function here. When you learn the action, you just learn directly. And this actually helps it to generalize better because like if you can abstract your start state and your goal state, you can get the same action for various kinds of situations. Okay, I mean, the same argument could apply for value functions, but value functions will generally take longer to learn compared to this state and goal method. All right, then we also have a memory method in order to retrieve our memories. And this enables you to do some form of world model planning because you use your past memories to form the world model. Okay, and you use multiple trajectories, like multiple parallel branches, to find out which path is better. So that is what I like to call sampling and filtering. If you look at the video that I did on like AGI. So this sampling and filtering means this, all right? In order to evaluate what is good, you just need to imagine like maybe 1,000 possibilities. Something like Doctor Strange, he imagined 1,000,000 possibilities and he found one that he could win Thanos. So you could sample some possibilities and then you just pick the one that is best suited for your own needs, right? So something like this sampling and filtering is in this memory retrieval, and it helps the system to actually self-improve itself to a certain extent because you can learn from the best experience that you retrieve. Okay, to a certain extent. Why do I say to a certain extent? Because you cannot learn from every experience. One person cannot experience every single thing in the world. It's just too many. So, but at least in that limited scope that you remember based on your memory, you can pick like the best path in your memory to solve the problem. Okay, so that's also why I would like to highlight that I don't think humans are optimal. Many a times you can get stuck in certain habits that make you do the same thing again and again, but that may not be the fastest. It's just that it worked before, so you do again. Stuff like, if you go from point A to point B, you may not take the shortest path all the time, right? Who here thinks that you always take the shortest path when you go from a certain place to a certain place? Anyone thinks that you always take the shortest path? Or who here thinks that you just take the path that you are most familiar with? Just raise your hand.
I'm going to go with neither.
Oh, nice. Okay, then what path do you take?
It seems most likely, often based on very little information or knowledge. I do get lost quite a bit. So it's dead reckoning and so on, but they don't. So I use other guesstimates of where I'm going and where I'm coming from. My hometown of Canberra is notoriously difficult to find your way around, particularly for driving. So it is a very ineffective way to find your way around Canberra. And so I get lost a lot.
Okay, so that means also it proves the point that we are not optimal. We cannot really like do shortest path planning and so on. So yeah, this memory mechanism is similar. You can probably only do stuff within what you have experienced before. So in Richard's case, if you get lost, it probably means you couldn't retrieve the right memory to get you from that point to another point, which could happen. Yeah. So yeah, moving on. This is the memory retrieval network. I think I will not go into the details. Please refer to my other video on it. So this one is basically you have a few branches. All right, you take the start state and then you reference memory of next state. So like you have start state 1, and then you take like a certain action A, you go to start state 2, and then from start state 2, you can sample another memory that takes another action. Okay, let's call it A2 to start state 3. So maybe over here you reach start state 3, which is your angle. Here you reach like 5, here you reach 7, which doesn't really reach the angle. And what will happen is because this memory reaches fastest because it's only 3, it blocks off the rest. It inhibits the rest, and basically what you will get is you get this sequence here of the shortest path, which is actually, like, I would like to say this is locally optimal based on what is sampled. You basically choose based on what you sample the fastest path, and yeah, from there you can actually self-improve a bit. So yeah, I do have a message. Let's see. I'm curious about the override behavior. Is it always or according to some metric? Yeah, it's always. Yeah, because in this formulation, the memory is the most accurate. The neural network is just a rough guide over here. That's why I mentioned. Okay, so the goal-directed neural network. So this is the interesting part, and this is the part that I like a lot, because this is self-supervised learning. Okay, why do I say this is self-supervised learning? So in self-supervised learning, what happens is that you take a certain state and a goal, and you predict the action. So this state and goal can come from your trajectory itself. So there are two trajectories that you have. So if you look at this mice over here, the mice start state is here, and then the current state is here. Based on hippocampal replay, it actually does a forward play and a reverse play. And traditionally, what people think is doing is that it backpropagates the values from the end state to the start state, like in the one-step Bellman update kind of stuff. However, I actually found another use for this. Okay, another potential use is that it could be training the goal-directed neural network. So given any start state in the trajectory, and then you just basically place the trajectory to the goal state. From this goal state, you can then condition the action from every start state to every goal state, and you can learn from this trajectory like that. So what could happen is that you fix the goal state here, and then you learn back to the starting state. Like each of these states here, you learn what is the action from this starting state to the goal state. So if we do this hippocampal replay at every step of the maze, you essentially learn all transitions, right? ABC, you learn AB, you learn AC, you learn BC. Okay, because like at time step 3, maybe you learn state 1 to state 3, state 2 to state 3. And then at time step 4, because now you are currently at state 4, you learn the state 1 to state 4, state 2 to state 4, state 3 to state 4. Okay, I mean, of course, that's time step 2, you also learn something. You learn state 2, state 1 to state 2. So if you repeat this like hippocampal replay for every single time step that you have, you essentially learn all the transitions and their first action. And this is self-supervised learning because you don't have to have human labels. Okay, the label is your own action. So if I step forward and I move a state, I learned that, okay, if I move forward, this is what's going to happen. This is my current visual view. I step forward, my visual view will be something else. So this kind of self-supervised learning is actually quite missing in reinforcement learning, because reinforcement learning, we typically go by rewards, right? And in rewards, the rewards can change over time. You can't really learn that very well. Okay, and actually there's a lot of reward hacking done in reinforcement learning where you introduce rewards to help to guide the robot to walk forward. For example, by saying that, hey, if you go sideways, I penalize you. Like a lot of things that are done right now in robotics actually are quite hand-tuned because the rewards, we want to make sure the robot does certain things. We just penalize it for doing things that we don't want it. We reward it more for doing things that we want. But it doesn't really learn it by itself. So this goal-directed neural network using self-supervised learning will be able to learn like based on any start state, any goal state, like what's the action needed. So it is very flexible because you don't have to have the robot or the agent succeed in order to learn something. Even if I fail or if the robot fails, the robot will learn something because it will learn how to fail. It will learn how to reach that state that it failed. So it is very resource efficient or sample efficient in your experiences. And another part here is that there's this part at the back, which does the look ahead replay. So this look ahead replay is something that is useful because remember just now we talked about the memory mechanism. You can learn from the best trajectory and then you can do you can learn from best memory. And this actually will help the network become more and more efficient or more and more like locally optimal. So yeah, you do the hippocampal replay for both the previous states and the future states. So this actually gels quite well with neuroscience literature. So this method, I think, has some neurological basis. Although in the literature, they don't talk about it like that. They talk about value functions, but I'm pretty sure it can be interpreted like this way as well, using the goal-directed manner. All right, so let me answer some questions. Kyren said, the beauty of the artificial general agent is that you can empty completely its memory. So your own human bad habits do not get into the way of better route. Like Bruce Lee said, empty your cup. Is that correct? Yeah, of course. If let's say, humans, we suffer from trauma, right? In certain environments because like you have some bad experiences. In AI agents, yeah, of course, if you see that it's affecting the agent, you could just empty the memory and you'll behave differently. So I like to tell people also, like you are who you are actually because of your memories. If I wipe away your memories, you may not make the same decisions again because you don't have that memory to help you guide your actions. Like this memory part here, we rely a lot on our past memories in order to make a certain decision or do a certain action. Like a lot of habits are formed based on past memory. And if you keep replaying your actions, eventually your fast neural network will also learn how to do this action and you don't need the memory anymore. So it's half true. So what Kyren said is half true. You can empty your episodic memory completely, but if it's already learned, okay, the neural network here, you may not be able to stop it. You might still react in a certain way because you have trained this network already. So if you want to empty, you might need to empty both. Yeah. So next,
Hey,
yeah.
Hey John, to follow up that question, see the reason I ask is that there can be a tremendous amount of opportunity in some of the psychological and clinical help with people who experience, dramatic experience, right? So in this case, if you already learn it and is in the neural network, can you do some sort of intervention like by human effort and try to clean it out? Is that going to be hard in that case?
Yes. I mean, how do humans know what is good or what is bad if there's so many experiences? I mean, you could pick out certain few to wipe out. But I would say that in this case, to answer your question, it might be better to just have a new agent that learns from the new environment. So that's also my philosophy for why humans die, because after a while, your network gets flooded with a lot of past experiences that may not be useful anymore. But it's very hard for us to get rid of it, of them. So the easiest way for like maybe nature to adapt is to have a new generation. Yeah. So I hope that kind of answers the point. I think it's very hard to curate what memories you want to keep, what you don't want to, unless you already know exactly what to look out for.
Yeah, makes sense. Yeah.
Yeah.
I think you talk about sort of surviving trauma and things like that. And people go with exposure therapies and stuff like that. They don't try to raise the memory. They try to manage the associations of them. So saying in the chat, like it's like uncensored large language models. It's an attempt to retrain the response to the same stimuli.
Yeah. In fact,
And
that's trauma
yeah.
management. Yeah, they recreate the same fear scenario, but they pair it up with happy associations, like maybe you get rewarded with an ice cream or something. Yeah, so you try to remove away the trauma. I think it's limited effectiveness, but definitely something like that could be trying to manipulate your memories. And yeah, later we can get into that because I do talk about emotions as one of the future plans. And yeah, you could do something like that to like sort of make certain memories more emotional so that you can try to override whatever that's there in the past. Okay, however, the fear circuit or the trauma circuit is so powerful that it may be impossible to override it with happy memories. So that's why trauma still exists. Yeah, so we can talk about that later. We have one slide on emotion. I think modeling emotions will be very important for fast adaptive agents because emotions can guide what memories are important. So we will talk about that later. Okay, Ray also asked, I saw a similar method to this goal-directed network in DQN. They call it hindsight experience replay. Very good. Good that you brought up hindsight experience replay because this is way better than hindsight experience replay. Hindsight experience replay only goes through to the goal state, the final goal state. But in this method, you can have any single state in the trajectory as your goal state. So you can learn way more than just hindsight experience replay. Yeah, and also the other thing is hindsight experience replay uses values. I kind of argue against learning values because it takes very long to update. And it doesn't change very well with changing goals and environments. Yep. Okay, so I think that's more or less the points. Ray also mentioned what Kaya mentioned could be possible and more important when LM becomes more used. Yeah, I mean, to be adaptive with the memory and stuff like that. I think that is a very important point as well for adaptiveness. How to have different agents with different memories. Okay, so here I'm not talking about the same agent, you manipulate the memory. I think in the same agent, it's very hard to do that, but you can get adaptiveness within a population. So we'll talk more about that later. Okay, good points, good points. Okay, I think you are also quite aligned with my future goals as well. All right, so this is the overall procedure using memory. And over here, the main thing is you have a goal state, you have a current state. Okay, you first use the fast neural network to get your intuition, to get your action. Okay, and over here I use action probabilities. Okay, because right now the current architectures uses probabilities. Okay, what we do is we take the probability and this will become our exploit criteria. And then in order to make sure that the agent explores more, we also have a term whereby if you haven't visited a new state, a new action, okay, we try to reward you by basically saying that, hey, the more times you do this action, I'm going to penalize you a bit more. So I try to make you explore to new situations. So this is the explore exploit thing. It works quite well in reinforcement learning. And I think this is quite important because, even for humans, when we eat like our food or lunch, you have duck rice and chicken rice. You don't eat duck rice all the time. After a while, you'll be bored of duck rice and you want to try chicken rice. So that means that maybe you have eaten duck rice too many times. This bar is very high. Okay, so maybe let me just explain this in detail. So like duck rice and chicken rice, right? So let's say your action probabilities are like the same, like basically is 0.5, PA is 0.5 over here, and then here is, let's say both are preferred equally, but then your num visits here is 3, is 2, and then here the num visits is 0. So you can see that the more times you do like duck rice, okay, after a while, the value that you calculate over here, if you plug in this into the equation, you will realize that this is actually lower than the chicken rice. So you will value chicken rice because you haven't eaten chicken rice before. So this complicated equation here is just saying that, if you explore, so you have done certain actions before, you will prioritize other actions. Okay, but of course, if your exploit term is very high, okay, you might do more of the action, a lot more of the action before you try something else. So this is the exploit trade-off in reinforcement learning. And this is what I think the system one does. All right, it tries to do some exploration and gives you some rough guidance as to where to go. All right, and okay, the next is slow memory retrieval. The slow memory retrieval is basically the memory look ahead. So if there's a trajectory from start state to goal state, we will override the action. Okay, so because system 2 is more accurate. So if let's say there's something different in your environment, okay, or rather for every state, we do a new transition, like the current state, the current action, and the new action. at the new state. So this will be stored into your memory as a tuple. Okay, we will remove all memories that conflict with the current transition, because like we don't want to use the past memories to affect it. Okay, but there's a new insight that I have here. If you can encode surprisal and retrieve surprisal memories more, you may not need to override. Okay, so I actually recently been thinking that maybe memory could all be stored. Okay, it's just that we have certain values given to each memory. Some memories are more equal than others, are more prioritized than others. So once you do the memory look ahead, you focus on those memories that are newer or like more higher value, right? And surprisal could be a very high value. So like when you see your doorknob in a different position, you might be very surprised the first time. And then the next time you go to the door, you will retrieve the surprise memory first. You're like, hey, the doorknob has changed. So, you could have both memories, doorknob at the bottom, doorknob at the top, but because you were surprised when the doorknob changes, you'll retrieve that surprise memory first. Okay, we can discuss more about this, but now I'm starting to think that we may not overwrite the memories. Okay, we may just have new memories, but we just store them more strongly so that we will retrieve them first. All right. So the memory update also means that like if you can find a trajectory, we can also do hippocampal replay to learn the system-wide network. Okay, so this is more or less the key way of doing the learning fast and slow. We learn mainly, okay, just a recap, okay, because this is more or less the last slide of the whole thing. Just a recap. We learn mainly the start state and goal state using and predict the action using self-supervised learning of the current trajectory and the future planned trajectory. Okay, the memory will help you to plan a better trajectory. Okay, and using both networks at the same time will help you to learn immediately whenever you have a new transition, because the memory will be updated instantly. Okay, you can do your memory planning here instantly. And eventually over time, this network will be competent enough such that even without the memory, you can still perform the action because you are so used to it. It's like muscle memory. After a while, you can play a piano piece without like intentionally remembering anything. Yeah, so this means that this network here has been trained. So you have both a fast system and a slow system. A slow system is this one because you need, okay, so the fast and slow is basically is a bit confusing, but this is fast to deduce the action. This is slow to deduce the action. But in terms of learning wise, this is very fast to learn. Memory update affects your actions instantly, while the neural network part will take a while to learn, all right? Because you need more experiences and so on. So I just pause here for like maybe 1 minute. And any questions on this? Because the next few slides, we'll talk about how to improve this. All good? Do you all understand this baseline architecture?
I think so. I've still got some questions around this, but they might come under the heading of optimization. So where we talk about confidence of this approach or that approach. And then because it strikes me that once you go through the memory retrieval and consolidation, you'll come back with some answer, good, bad, or indifferent. You don't, but
yeah,
you should have intuitively, your memory should tell you how close this is to the last time you had to solve this problem. Right? I don't know how yet, but that's another matter. So it should come back with a quality of solution. In principle, it's harder to do that in the fast neural network model because it doesn't have experience as such. But this is where I was asking around if the override is conditional or always or what have you, because I see there's a qualitative difference in the answers. I mean, if they're quantitatively the same answer, easy. Everyone agrees, we just go ahead and do it. But if you see what I'm getting at, it feels to me like, when do you default to your best guess and when do you go, no, this is a terrible guess, we're going to do it anyway? Like me navigating in my hometown. So,
yeah, so you're saying that there could be memory paths that are similar that you can still use.
Yeah, I mean, we in the Discord chat, I sort of alluded to this idea of, is proximity or explicit relationship necessary? And that's a different matter. But the thing is, more often than memories being a perfect match, you'll have an imperfect match which is still useful, right? Which is the whole, like your goal-directed learning. That's the whole sort of premise there, right? It's not perfect, but it's good enough to get started. And so I think that'll be the more common case than a perfect match, also because memories are so variable. But on the other hand, you've got intuition, where it's always imperfect, but you don't have really a clue for how imperfect. So you go to your muscle memory question. Right? I used to do some martial arts decades ago, and I can tell you that drops off real fast. Right? And it's not a reliable way to get things done if you've lost that muscle memory. Right? So I know that if I was to walk back into a training class, I'd need to really slow me down first of all, because I cannot do the things I remember doing. Does that make sense? Right?
Yeah,
So
I mean, your muscle memory might be there, but your body cannot execute it.
no, they're both gone. Trust me, it's all gone. And so there's some elements of my muscle memory that are present because they're things that I've been able to keep up with, but there's other things where physically I can't do it because I'm weaker or not properly conditioned or what have you. But there's other things where it just isn't there. There's nothing there to call on. And so, in a martial arts context, punches and blocks are sloppy and slow and misplaced and all the rest of it. But that, and I had to learn that. That's my memory kicking in. One time I went back to a class and went, wow, I'm really bad at this now. I had to, that's my memory says, don't trust your intuition. It's wrong. Right. And if that makes sense.
Correct. So that's why I like the idea that your memory planning could override or should override your intuition, because this is more accurate. Actually, it goes through, it's like a search tree. So the right side involves a search tree, the left side doesn't. All right. So there's one point that I like to say, because the stuff that you said that your memory path might not be exact, but it might still be useful. I think that is a very good point. Okay, right now the system does not cater that into account, but once we could have certain ways to gauge how close you are from your goal state to your start state, maybe you could use that trajectory as well to give you the action. So there could be more complicated ways of getting this memory retrieval, which could take into account memories that are not exact match. And I mean, one way to think about it is like retrieval augmented generation. When you retrieve chunks in like the current neural network, you have context 1, or I mean, I like to call it memory 1, memory 2, memory 3, but let's say context 1, context 2, context 3, and then you have your query, right? So you can see that in the retrieval augmented generation, you may not have the retrieve context being exactly the same as your query, but it's similar due to cosine similarity. You embed and you retrieve it, then you get an answer. So this answer could be this action here. So perhaps we could do something like what the neural network is, large language models are doing. You have different kinds of memory here, and then perhaps for each memory we can say that, hey, this memory did not go to the goal state. You just put the trajectory there, like it reaches state, this one reaches state 4, this one reaches state 3, this one reaches state 1, and so on. So if let's say your query is like, how do I get to state 2? So these are the most similarly retrieved states. Maybe you can embed your states and you retrieve cosine similarity your states. You could use something like that and some form of attention over the past memories, and you get your action out. That could be one way to do it. In this case, there's no lateral inhibition. The original idea is that you have a fixed path here. You laterally inhibit all the rest because you don't need to use them anymore. You found a path. But suppose you don't have an exact match. Maybe we could use something like that. So this is the use similar memories if no exact match found. Okay, how to do this? Maybe we use a transformer or use other methods that could do this. Is this something like what you have in mind, Richard?
I think so. I mean, that's what I mean. It sort of falls into this general bucket of optimization. And so it's but also at the same time, we say it's a near miss, right? How near is near, right? And the idea of the quality of a solution as well as, well, there's qualities, there's lots of things, but in one case for memory, it's how exact is this memory, right? And so you go, well, and perhaps how recent is it is another question, because you're talking about the usefulness of dying, right, so far as memory goes, but also your memories fade over time, which leaves you more context, as it were, to work with in the current state. And so how I used to navigate my hometown when I lived there is actually not that important anymore, right? I can focus my mind on more relevant problems to today. So I think there's a couple of different metrics, for want of a better term, that talk about quality of a memory and quality of a solution. And I guess that's where I'm sort of, but they really come down to optimization, right? So the fundamental principle remains exactly like this, but each of the steps, there's a question of quality and newness and stuff like that, if that makes sense.
Yeah, each memory should be referenced in priority based on how recent it is. Like the recent one should override the past ones as much as possible. So there could be some form of value decay in the memory. Like after a while, your memory just like goes down in value. Then whatever new memory you encode will be a higher value, something like that. Yep. So I don't know whether.
And we talked another thing about quantization as a way to mash memories together, so you end up with more useful memories, even if they're not strictly speaking accurate, if that makes sense.
Yeah, so this is about how the current memory in our human minds might be like kind of updated based on the current stimuli. When you retrieve them, it may not be the original memories. That's what you're talking about.
That too, yeah.
Yeah, so that's what I was thinking about also. But I feel that the more I think about it, the more I feel that this might be just a limitation of the human mind, because we just don't have the capacity to store so much. Or maybe that's useful. We won't know until we model it out. But what I'm thinking is that, you could just store everything for now. Okay, because technically the computer memory is much more than the human memory. We can store way more. So there's no reason to like change our past memories to make them less accurate, like what we do in the human mind. We may not need to do that for AI systems. Yeah. The other point you make about state abstractions, like how do you know how useful this memory is? Like we can see how close they are in some embedding space or some abstraction space. There might be more than one abstraction space and so on. So I do think this is very important, because we aren't going to do grid worlds in the future. Like grid world is just an experimentation. The state and this goal should be some high dimensional vector, and you need some way of knowing how similar your goal is to this goal that you get in memory. So I do quite like the idea that you mentioned about like, oh, you might have to have some form of a way to match them. Yeah. So that would be under abstractions. Okay, cool. All right, let's move to the future.
John,
Yeah.
I had one question around like memory always overriding the slow network always overriding the fast network
All right,
action.
please.
So yeah, I mean, so I'm just taking an example of like, so if we deal with like we walk every day, right? And when we are walking, we don't really invoke the slow part of our memory and ask like, how do I walk, right? I mean, it's more of a muscle memory. And yeah, I mean, if we think about it, like if we were to invoke our memory part more, it would be a pretty awkward walking. Like, what's the next step should I do? I should first like move my left leg, then right leg. So it seems like we are not overriding the fast network always. So do you think that's just the imperfection of human mind or limitation of human mind? Or is that more there that not every memory can be retrieved, so that muscle memory, like we can rely on the fast network sometimes?
Yeah, in fact, actually, most times we are using the fast network. We only need to use the slow network like very, very little time. When you are in unfamiliar scenarios, then you need to try to find a way, or like something changed, then you try to think about, like, if you walk and then you see an obstacle in front of you, you start to think, hey, is there another way to get there based on my memory and so on. So that is when you trigger the memory. But if let's say everything is smooth sailing and you're very familiar with it, and then this is your default network. So I do think that we don't use the look ahead that much, because or if we do use the look ahead, it happens so quickly that you don't really perceive it. Because why we don't want to use this this actually is quite I think this drains a lot of energy. So like when I do math problems, I can feel like I'm using this network to do look ahead, because like I'm trying to think of what's the potential paths that we can solve it. Or you play chess or I play Go, you use that network a lot. I feel very hungry after I play Go, because I need to think quite a bit. And that is a reflection of how much energy it uses. So I think if we keep using this look ahead network, we will not survive. Okay, it just takes up too much energy. But that being said, AGI computers, all right, can use this all the time because they have quite a lot of energy. So I don't think we need to necessarily model like how efficient we are in terms of like only use the fast network most of the time, that's slow sometimes. Like capable computers in the future can just use the slow network all the time. Yeah, they'll be better than us. If that answers the question.
Yeah, makes sense.
Yep. Okay, let's go to the future plans, okay, because that's today's session. But thanks so much for asking. So anyway, this is the conclusion for the slide. The main thing is don't use value systems much. Okay, if you just do goal-directed action prediction, it's much faster to learn and it has the benefits of being self-supervised. These values-based systems are usually hand engineered. So it's not that great. Yeah. Even for intrinsic reward, it's also hand engineered. Yeah. So how do we do memory? Okay, memory is robust. Okay, memory adapts faster than neural networks. And of course, how to encode and how to retrieve memories are very important for learning. And we'll talk about that more. Right. This next part about probabilities, I have different people tell me different things. Some say yes, we still need probabilities. Some say no. I do think that probabilities are not innate to the human mind. All right. But if there's some system that could approximate probabilities like sampling, then yes, surely we can do probabilities. So I do think we just need sampling. So this is my point of view. Okay, let's not go into debate about this because this part doesn't really concern too much about the architecture of the future. But I'm just saying that probabilities may not be the focus of this kind of fast learning systems, especially since the number of possible states are potentially infinite. We just need to do pattern matching and sampling to the most closest pattern match. You may not need the probabilities anymore. Okay, now let's move on to today's key point. All right, so what is this 10-year plan? So I'm very interested. My life goal is to create fast learning and adaptable agents, and I'm very unhappy with the current state of the art. So this plan is a plan to get there, okay, to get to a future state whereby agents or artificial agents are able to learn and adapt just as fast or even faster than humans. So we don't have to like, hey, train an agent in this environment A and only use in environment A. The agent should be able to learn in various different environments. And even if it hasn't seen an environment before, it will still be able to adapt there. So that's the idea. Okay, so what are the main things to do? Okay, so the first improvement is something that is quite immediate. You can see the effects already. You can do a goal-directed decision transformer. Instead of just having one single state, you could have all the past states here as well. State 1, action 1, state 2, action 2, and so on. So using this decision transformer, you are able to use your past trajectory and do some form of attention over it in order to get your action. So there will still be a goal here. But instead of just having the current state, I can use the past trajectory of states, which might make it more effective. Because I know, hey, I've gone from south to north. I don't want to go back to south again. I might go somewhere else. So that might help with exploration as well. So next thing is other memory types. Okay, so like, for example, we don't just have episodic memory. Right now, this memory is episodic because we do the state transitions. So right now, it's mainly episodic. But we might have memory such as a semantic memory where you have facts, some facts that you might learn about the world, like John is tall, or like Eiffel Tower is in France. It's in Paris, maybe. Yep. So you might learn stuff like that. This might even be encoded in some way, in some semantic ontology like knowledge graphs. I don't believe we have knowledge graphs in our heads, but you could have some relation of like this chunk to another chunk, like in a loose way. So perhaps we could have something like that. Why is this important? Okay, because sometimes you may not experience things. We have evolved, humans have evolved to the stage whereby we don't need to experience it personally in order to learn from it. We could just hear facts about it or deduce facts, and then by some inference of this, we can extrapolate to conditions that we have never seen before. Take for example, I tell you that ice is cold. You know for a fact that ice is cold. Then when you go to a place with like you see ice on the floor. So what do you expect? You expect that the floor is cold, right? Yeah. So you have never seen ice on the floor before. Maybe ice is an ice cube, but you see that ice on the floor, you can extrapolate, say, hey, that'll be cold, right? Although you have never experienced it before. So this other memory types allows you to. This is basically what I call reflection and consolidation to extrapolate to other scenarios. So I think this is something that could be built in order to learn more. Okay, the memory that you have is not just episodic memory. You could have other semantic memory as well, so that you can do inference and use it to extrapolate. So I think this is quite I mean, at least this is how I view it. Okay, we can discuss more about like how you view it as well. Okay, but let me just go through the rest of the slide. So we also have emotions. So emotions is basically, that's why I said, like you could have some memories that it's surprisal, you retrieve it more often. Okay, happy memories, also retrieve it more often. Okay, so happy or fear, all right? So very extreme emotions. Emotions will guide you as to what memories to take. And because this is very important, if not, we experience so many things in our lives. How do we know what memories are important? So I would say that we have a way to encode importance using emotions. So a lot of people like, Jeff Hawkins say emotions are not needed. Yann LeCun says emotions are needed. I'm in the Yann LeCun camp. Okay, I think without emotions, you have no way to prioritize your experiences. And that is very difficult to learn. So how do we learn emotions? This is later we can discuss this. My view is that emotions are not learned. They are just given to us. So yeah. So basically we have a fixed set of bias, and the emotions could be one set of bias that's given to us in order to enable us to learn better in the world. All right. So the other things that I like to talk about is like we could have various ways to do goal planning. We could have abstraction spaces to do like macro planning to micro planning, and we could have multiple such spaces. Okay, and the abstraction space could also be grouped by proximity. So I will cover this more in detail later, so I won't talk about it now. But this is basically saying that we can plan at different levels and we choose the best kind of abstraction space or abstraction spaces in order to solve a problem. This is very similar to my abstraction and reasoning corpus, the ARC challenge, whereby I have like the grid view, object view, pixel view, and I just choose the best view, and that achieves like world record solve rate, like 45% in over one-on-one problems. The next best is I think about 30% on the solve rate. So if we have multiple abstraction spaces, I think this is much better for planning. Okay, we don't just want to plan at one scale because different problems require different perspectives. Okay, like I like to use the example of an image with a dog and a frisbee. So let's say you have a dog over here. Okay, I don't draw very well, but let's say this is a dog. Okay. And then you have a frisbee here. So you could ask questions like, like where is this? So this one will be like you need to know the scene. You ask a question like what is in the picture? And you need to have like dog, frisbee. So this one is object view. Okay, and then that's right here. And you can also ask like what recreate the scene. So then you will need to know exactly where the pixels are. So based on the questions you ask, you might need to retrieve different parts of the image, and you won't know beforehand what is needed. So if you only store at one view, like you store at the pixel level, you might miss out the details of, hey, there's a dog there, there's a frisbee there. You might miss out the object stuff. If you store only the objects, you might miss out that, hey, this is actually in the beach. You may miss out the overall view. So there are different ways to store information, and I think we store at all kinds of levels. Okay, not all the levels, but sufficient enough levels such that you are able to go up and down the hierarchy in order to zoom in or zoom out to solve a particular problem. And that is what is missing in most architectures today. We don't have this kind of multiple abstraction spaces. And I think this is very important in order to solve intelligence. Okay. And the last part of today's talk will be, or discussion will be about how to do this in multiple agents. Okay, how do we transfer memory? How do we do it between different senses? Because I believe this is not just a single sense, but all the senses combined: vision, audio, location, and so on. All right, that's all the summary for the 10-year plan. Okay, do you want to ask any clarifying questions first before I go into one by one? Okay, let's just ask the questions while we go through the slides, all right? So first, the goal-directed decision transformer. So I think this is rather straightforward. So instead of just having a state and a goal, our state could encompass, okay, the previous states and actions like that. So the decision transformer basically takes in like the rewards to go, and the current state, and outputs the next action, and the next action will come here. Okay, what I propose to do is, instead of the reward to go, we put in the goal state. Okay, so we have like a current state here, a start state, and we have a goal state. So our action will slowly lead us, to the goal. So we basically predict the next action until we reach the goal. And this is likely going to be more powerful than just a single state alone, because you have the past sequences, you have the history, and this history could help you make better decisions. So this is the goal-directed decision transformer. I did some experiments on ChatGPT on this. It works way better than reward-based methods. Okay, haven't had the time to write a paper on this. So if you are interested to write a paper on this with me, let me know. All right, so I'm very sure this will work. So this is called the goal-directed decision transformer. Questions on this? Okay, so this is quite clear, right? All right, next I'm going to talk about the abstraction spaces. So Yann LeCun has this paper called A Path Towards Autonomous Machine Intelligence. And in it, he talks about this thing called the hierarchical joint embedding predictive architecture, which basically means that you plan at different levels of hierarchy. The top level of hierarchy could be something more broad, like, go to school. And then like the next action will be like eat breakfast. And then like at the lower levels, the action space could be even lesser. It could be like take bus, walk to gate. All right, and then like eventually the last part would be motor action. So eat breakfast would be buy from store, eat. Yeah. So you could have different like top level to bottom level, and then at the bottom here you have motor actions that you take in the environment. So I do like this level of hierarchy here. Okay, what I don't like about this architecture is that it's an optimization based to minimize this cost. And his cost over here is actually the internal displeasure. So you're trying to, or discomfort. You're trying to minimize discomfort based on some intrinsic costs that are like maybe given to you at the start, or is learnable. So there's both costs. And I do think that if you do like this cost minimization, you try to optimize this, it learns very slowly, as what you see in value-based methods. I said earlier, the value method takes a long time for it to learn to converge, right? But he likes it. He calls this the model predictive control. But my view is that takes too long to learn by optimization. Okay, we might just need to do better metric. Okay, so this is my only gripe with the method, but I do agree with this kind of hierarchical way of doing things. Okay, so Hardik mentioned on hierarchical JEPA, how do we define fixed steps on hierarchy? Should that not change with goal? How do we define fixed steps on hierarchy? Oh, how do we define the hierarchy? Is that what you're asking, Hardik?
Yeah. I meant like how many levels should be there in the hierarchy.
Correct. So he did not mention that. And that is a problem that I will address in my next few slides, like how to get the hierarchy. So I've been thinking about this problem for months. I think I've got some answer already. So good question. Yann LeCun did not mention that in his paper, how to get the hierarchies. But let me go through how we might get the hierarchies. Okay, this is not the slide for it, but this is how fast and slow could relate to hierarchical JEPA. All right. So same thing, we have sequential and hierarchical blocks. Okay, so this is the fast and slow architecture. We have a state and we have a goal. And remember, you have your fast neural network here, your state and goal here. This is the fast neural network. And then we have the memory retrieval here. If you remember how the diagram looks like, right? You have the memory retrieval part here. So both of these things, okay, would contribute to an action. So this is basically the fast and slow block. Okay, I just omit the internals, but this is the fast and slow block that we saw earlier. We have a state and we have a goal, and we get an action out. All right, so this is the catch. All right, this action that you get out over here, okay, may not. So as you know, we could plan right at the lowest levels, which is like move your left leg, move your right leg. Okay, so there are different levels of actions, like different tiers of actions. So it's like move left leg, move right leg. That's the most micro. I mean, the most micro will be which muscle group, right? And also we have like move to square A, move to square B. All right. Then also we have other things like move from CP1. Oops. Move. Okay. Never mind. I'll just write here. Move to CPA, move to CPB. And after that, we could have like move to country A. Okay, can anyone tell me in this list of actions, how are the actions related to one another? And anyone? Just looking at the actions alone, how is this actions linked in this red arrow downwards? Anyone can tell me?
It's generalizing. It's becoming more broad in its scope from the
Right.
specific to an individual, or not even all of them, all the way through to, as you say, much higher level of abstraction or generalization.
Correct. So this also links to like how Hardik asked, like how the abstraction is formed. I believe, okay, that the abstraction is formed by proximity. So you look at here, like these actions here, move left leg, move right leg. Okay, this in terms of state space, this should be like that. State 1, move left leg. State 2, move right leg. So it is more like, let's call this A, transition A. Transition A is more like one single transition. Move to square A, move to square B, maybe you need a lot more. So this whole thing here is transition B. You can see that it's a sequence of A actions. All right, then if we talk about like move to CTA and CTB, you know, it might be even more complicated. It might be like that. And then once you go to country, you know, your D, I'm not going to draw it out, but I'm just going to draw an arrow for D. The D could be like that. It's a huge, humongous arrow because like it covers a lot of states. So what this means is that perhaps the hierarchy is just formed by proximity of the states in the embedding space. So why do we need to have different levels of states? All right. Why not just do everything in the move left leg, move right leg era? All right. This has to do with planning. Okay. The more steps, the worse. So I mean that's true, right? If you think about it, if you need to like do some form of like let's say you play a chess game, you need to think 100 moves in advance. Who can think of 100 moves in advance, right? Like even the best chess masters, I think maybe they only think 10 moves. Okay, I don't quote me on this. I don't know, but you know, it's hard to plan so far in advance. Like it's easy to plan if let's say you know, okay, if I move my hand to here, I can pick up my cup. That's like instant. But let's say if my cup is very, very far away, I need to think of like, oh, I need to go to this room, need to go up the elevator, go up the stairs and pick my cup. And it gets harder and harder to plan. And you know, I have a kid. His planning is quite short term. So he sees a toy, he will run to the toy. But if he doesn't see the toy there, he might not be able to know where the toy is. But now as he grows older and older, he's able to find out like, oh, the toy is actually in this room. I can go here and take it. Yeah. So the more we grow, you know, the more capacity we have to plan. But in general, if we plan everything at the lowest levels, you know, it's not going to work very well. Right? You can try it. You try to plan your daily life with move left leg and move right leg. You see how far you can get. All right. So the thing is, after we can like group things by proximity, we could have the higher levels being more abstract. Okay, and this is basically the idea of hierarchy. So if we could get more abstracted actions based on like what you have done in the micro level, you can plan at the abstraction space. So you could plan, instead of move left leg, move right leg, you can plan like move to square A, square B. I think that is a much easier way to plan than to plan the motor actions. And then if we go more and more, we can say move to choke point A, move to choke point B. Okay, so what is a choke point? Okay, so in a grid world, okay, in a grid world, if you have rooms, right? Like say in your house, you have rooms like that. So your agent is here. This place, I can call it choke point A. This place, I can call it choke point B. Okay, why is it a choke point? Because if we want to get out of the room, all right, let's say this is the goal. If you want to get out of the room, you'll find yourselves being in this state more often. Because a lot of different trajectories, okay, will go through like one of, like you can go through like that, but all of them will go through A. So if you go by proximity, you will realize that you can split this whole grid up into this area. So this is like maybe area 1, and then you can call this part here area 2. So instead of planning squares, you can just plan area 1, go to area 2. All right, and this is a next level of abstraction. And how do we get this abstraction? Do we give it from start at the beginning? Is this hierarchy given? Okay, my answer at first was yes, but now I think it's no. This hierarchy is learned. All right, we learn it through our experiences. So if a lot of states pass through this A here, eventually we learn that, you know, this is an important point, okay? And then we can basically say that, all right, I'm very confident that anywhere in here, I can get to anywhere in this 1. So this can be region 1. I'm also very confident that anywhere in 2, I can get to anywhere in 2. Okay, but from 1 to 2, I'm not that confident because I don't have that many experiences there. So maybe because of that, you could have a way to say that, you know, I have 2 groups now. One is 1 and one is 2. So if you talk about it in a graph format, all right, your area 1 could be all linked like that because your area 1 is very easy to form. But this is area 2. Area 2 is also very easy to form, very easy to link between the squares because there's so many possibilities, right? Very, very interconnected. This is area 2. But between area 1 and area 2, there's only 1 link here, or like 2 links here. So this is like maybe a choke point A and this is your choke point B. So by proximity of like how it is, you might be able to group things together and say like, hey, like within 10 steps, I'm very confident that I can get anywhere here. Within 10 steps, I'm very confident I can get anywhere here. Then you can group the 2 groups together. So you might be able to group the goal states or group states by proximity. And this proximity groups can form next level of hierarchy. Yeah. So this is an idea that I've seen in like hierarchical small worlds, navigable small worlds, HNSW. I've also been talking to Zadik, one of the presenters at ICDL, the conference I just attended. He also did something like this about group state proximity-based abstractions, where he just says that, oh, there's a parameter K. Can I reach a certain state in 3 steps? Can I reach a certain state in 5 steps, in 7 steps? And then you can have different layers of hierarchy based on like how much proximity you want to limit to. Yeah, so I think something like that might be able to solve the hierarchical problem. We just go by proximity. So the key thing is now, how do we form this proximity metric? We need an embedding space. How do we store this memory? So again, these actually are similar things because if we can get the abstracted goal state, we can get the abstracted memory because you can get in your abstraction space, you could have like S1 abstraction. Let's call this abstraction. We put an alpha here. We have your action 1, abstracted action. And then you have your new state 2 abstracted. So you could store all this in an abstracted memory like that. Okay, and the good thing about this, okay, which I will talk about in the next slide, if we talk about the memory soup idea, all right? the abstracted memory space and the original memory space, because it's still using the same embeddings. Okay, it's just that, you know, one is more macro term, one more micro term. You can store all the macro and micro all in the same memory, which means, okay, that if let's say your question is asking about how do you get from macro state 1 to macro state 2, you can retrieve the macro state memory. If your question is asking how to get from state 1 to state 2, you can retrieve the normal memory. So all these memories could all be formed in the same memory soup. And I think this is very important, because that means at every level of planning here, okay, my action space, okay, which is approximate to like SG sub goal, right? My action space here, very important point here, okay? The action space is not constrained to hierarchy. Okay, your action space will be a function of from state to goal, what is the best match in terms of the action. Okay, if the best match is a long action, a macro action, then the output of this sub goal here will be will be more of a macro action. If the best match is like a single micro action, then the output will be a micro action. And there's no restriction as to like, oh, this level of hierarchy only can do macro actions, and the bottom level can only do micro actions. No such thing. Okay, if you need to do macro actions at the bottom level, go ahead and use the macro action. If you need to do macro action at the top level, go ahead and do it. So the idea of the memory soup is that you can use macro or micro actions anywhere in this chain. Then eventually, when you reach the micro action, which is here, you keep working it until you get the micro action here. This will be what you do next. This will be your next time step. So this action here is the motor action. Okay, so I think I need to explain a bit of this hierarchical stuff here. Okay, because right now we have a state, we have a goal. We perform an action. It can be micro or macro action, but we can combine this state and action together to get your next sub goal, which will be the goal for your bottom layer. Or we can get the next state, which will be the sequential planning. So eventually, let's talk about this layer first. Eventually, after we get your next state, and then we do your goal, once our final state becomes the goal itself, we are done with the planning. We have found a start state to the goal state. Okay, of course, if we talk about non-exact goals, you can get a similarity score above certain threshold between your state and goal. And then you can end your search there. Downwards, okay, we talk about downwards, you have this sub goal here. This sub goal will be basically like, for example, if you talk about, okay, let's give you an example. Like you start with square A, and then maybe your sub goal is square C, and then you go to square B. Okay, but in order to go from square A to square B, you might need to go from square A1 to square A2 to square A3. Then you go to square C. All right, so this means that I can have square C here. Okay, but I haven't found the most micro level action yet because I haven't reached the bottom, right? So then I continue down this chain here in order to reach the bottom. So over here, we keep doing and doing and doing until we reach the final action, which is like state 1, A1 to A2. All right, so at each level of the planning, we just basically choose the best macro or micro action, and then we keep doing it in sub-steps and so on until we reach the final action space. And I think that is more or less how hierarchical prediction is done, at least based on what I think right now. Okay, I think this is a very, very heavy slide. Okay, because this is huge. Okay, so if you talk about this sub goal over here, this sub goal could be square C. So square C could be the sub goal here, and the start state here is like square A1. And then we keep doing until like maybe here is square A3, right? And then once we finally reach our goal state, which is square C, okay, then we can exit this low level planner for the first part, and we can go to the next level planner here. Yeah, so yeah, and in this case, if we talk about this analogy here, this sub goal will be square B here. And we keep doing the next few states until we finally reach square B here.
Be clear that the expectation here is as an explicit move from the more detail, the more concrete to the more abstract. With every attempt at planning, you always choose for the most abstract goal or the most concrete goal.
I think what needs to be done here is that we just need to choose for a goal state that is the most similar.
Okay.
The next state to be the most similar to the goal state. So if the next state that is most similar to the goal state, it is a macro goal or it's a macro action, then the action will be macro action. So I think at every step of planning is just pattern matching to see what. Yeah. So basically, once you get the sub goal to be the macro action, the most similar state might be the small level actions. So there's one thing I'd like to add: the actions to reach a goal should be smaller in magnitude than the state to go itself. Okay, so I'm making a sort of assumption here that the goal itself from the state to the goal, to reach that path, you need to have smaller actions to reach there. So of course, this assumption might be false if, let's say, you have state here and your goal is here, and you actually need to reach here first, then you go to your goal. So still thinking about it, but we should limit the action space that we search for a current goal, for a current state to a goal. If not, what might happen is that we might go in loops. Yeah, so this part I'm still thinking about it, but I do think the action space is flexible. It can be macro action or micro action.
Hey, John, this sounds really great. Quick question. This implies that we can have concurrent action paths, right? Say, for example, I think which can relate, like in the old times, when you drive a stick shift, there are multiple actions has to happen concurrently, right? You have to release the clutch and then shift the gear. So in this example, the agent can actually do things concurrently, combining the macro and any of the micro actions, right? Am I correct?
Yes, so it can concurrently decide to do a macro action, which is like go to square C. But in execution, you only execute state A1 to state A2 because, at every point of time in the environment, we have to be bounded by the rules of time. So, you cannot just jump from A to C straight away, even though that's your plan. You need to do this basic step first, which is like in this case, you move your left leg or move your right leg. So while in your head, you might think that, okay, this is my macro level plan to go to square C. The mini plan is to go to square A2. You can execute out your mini plan like that. And only the mini plan will be seen by other people. They won't see like, oh, I'm going to square C, because that is internal to you. When you execute out your action, only the most smallest action, which is like for that time step itself, will be executed. So I'm not sure if that answers your question. You only execute the most basic action.
Yeah, you did. Yeah, I got it. Okay.
Yeah, but if you have multiple modalities, right? Let's say you want to walk while singing, your action could be both the walking and the singing. So if you have different modalities, you could do all of them concurrently. But I'm talking about here is just one modality.
Yeah, I see. Yep, got it.
Yeah, actually, even for like modality like muscle movement, right? You might actually be able to move both hands at the same time, right? Or like move your leg. So there might be ways of doing parallel actions together. Okay. So in order to reduce the complexity here, I'm just saying that, okay, maybe this action is talking about just purely this thumb or this finger, or your leg, you're just one action of the motor. Yeah. So of course, what could happen is that your action space here could be parallel actions to multiple actuators. I'm not saying that you can't do that. You can. Okay, just that it's going to be a bit more difficult. That means you need to have a separate parallel prediction to each muscle group, which is possible also.
Yeah. So say, for example, if you have a case like, learning how to serve in tennis, right? The speed that you toss the ball and the speed that you bring your tennis racket to the back and strike it at a point where it's just about to fall down, that would probably be better to learn from imitation than from pure analysis, right?
Yes, so that's why people who never learn formal tennis lessons or like swimming lessons, they might find it like hard to swim or hard to play tennis. So if you don't see other people play it, or you don't take formal lessons on it to guide you step by step how to do it, it might be impossible to learn the action. Let's take for example backflip. I don't know how to do backflip. Okay, even if I see someone do a backflip, I also don't know how to do it. So maybe in this kind of case, you need to like guide it slowly. You need to do like half a flip, 3/4 flip, and you keep doing and doing and doing, and eventually you'll get it. Like you can start with a height of like 0.5 meters and you backflip, then you go 0.4, 0.3, 0.2, and so on. So that is a kind of thing that I think you can't exactly learn from your own actions. Sometimes you might need guided learning. So yeah, you're talking about something that yeah, some limitations of own experience learning. Yeah, you may not be able to learn everything.
So that means self-supervised learning might not be sufficient, right?
Yes, for humans wise, if you want to do some tasks, you may not be able to learn just from your own experiences. You might need to learn from others, and not just others. You might need a guided way of learning so that you get the right transitions in you.
If I can, there's sort of two hurdles here, to use them, stretch the metaphor. One of them is to imagine a backflip as possible, right? So first of all, if you've never seen one, you may not ever imagine a backflip as a thing a person can do. So a failure of imagination, and you don't get any further because you never attempt. And that, that's a showstopper. You're not going any further. The next problem is if you imagine it's possible, you've seen it happen, then particularly with a backflip, you get that wrong, you break your neck, you can die. There's some pretty bad consequences. There's some downside risks here, right? Right. So downside risks being what it is, you really do, like, there's a fundamental problem with trying to teach yourself. That said, if you can imagine it, I'm sure that the first person had to teach themselves how to do a backflip, right? And the first person to survive that process could then show others what a backflip looks like, right? So like that's I think, we're talking about efficiency of like one of them is pass fail, right? Can I imagine it? The other one is about efficiency. So I think it's important to keep in mind the consequences of this or that strategy, right? And I think we've mentioned before, John, this idea that, how do you make a curriculum? How do you figure out what to learn is actually a really big question. And JEPA has this structure has some ways you can derive a future, but it's to imagine a future is actually in many ways the hard bit. The other one just takes time and effort.
Right. So I think it's great points here. So curriculum may be needed if naturally we don't encounter certain transitions. Okay, and this is valid, and that's why I think intelligence is not just a single person, it might be a group thing. So the more knowledgeable ones might spread their knowledge to the less, those who don't know how to do it. And definitely internal motivations play a huge part, because if you don't know that goal is possible, you won't even bother to try. All right. And of course, backflip is a very dangerous thing, and it doesn't exactly go in line with our own internal like motivations. Our internal motivations, there's nowhere in there that says I want to do a backflip. All right. It's more like, hey, do I have enough to eat? Do I have enough to drink? Reproduce and so on. There could be some internal motivations baked into us that helps us to define what this goal is. So there's this part about what are goals. All right. I think it's good to talk about it right now. Like, how do we define goals? And I think the goals that we have, right, are very heavily influenced by internal motivation. And I don't want to use intrinsic motivation because it's a different thing in reinforcement learning. Internal motivation mean set guidelines, like maybe like food, water, reproduction, and so on. Yeah. So like some people talk about money and power, but actually all these are also related to the earlier goals, right? Because
I looked at hierarchy of needs as my sort of model to work from for this same purpose, right? And it works pretty well. It's used in some computer games to provide behaviors.
Correct. And one other thing is the goal should be imaginable. Okay. Because if you cannot imagine something, how do you go towards that? All right, let's say we talk about going to the moon. All right, people can imagine going there because we can see the moon, right? What if I tell you our goal is to go into, like, go to Pluto or something? Okay, it can be difficult to imagine that if we don't already know how, like, planets look like, or like where is Pluto and so on. I mean, right now we can still imagine it because we know it's part of the solar system and so on. But let's say if I say I imagine to go into a quantum particle, like, can't really imagine that, right? Yeah, but we know quantum particles exist, so we can still, like, sort of form a reasonable thing to the goal. So what are goals that are not imaginable? Are things that we don't even know exist. So I don't know. Let's say there's this hypothetical ray called the V ray. Okay, we have X rays, right? Let's call it V ray. Okay, we don't know that it exists. So if our goal is to engineer a V ray, it's like, how do we do it? Because we don't even know how it looks like, whether it exists or not. So that goal is not very imaginable. So other goals that can be imaginable, but we don't have direct access, is like, how do we get AGI? Okay, so people know what AGI roughly looks like. Or actually, we also don't know, but we know, like, it's going to be, like, good at a lot of things. But how do we get there? People also don't really know, but we at least have that goal that we can imagine. So I do think the goals here have some limitation. It's limited by our imagination, actually. So if you can imagine something, you can likely make it as a goal. Another thing is maybe the goal should be feasible. Okay, I mean, you can imagine something, but there's no way to do it. Let's say if my goal is to say I want to time travel to the past. No, that's a goal. Yes, you can imagine that, but is it feasible? Not really. So how do we define these goals? Okay, must have some kind of restrictions and, something to do with our internal motivations. Okay, I haven't really fully thought about how to get these goals. This is an open question, but I do believe humans are goal directed. Unlike, we don't exactly seek reward all the time, because, like, reward is actually a kind of goal as well. Okay, but that kind of goal is more because we don't really know how, like, this internal motivation works. We just put a value to, like, hey, I eat a burger, I get a reward of 2. We just put a value there because we don't really know how the goals work. We just give an arbitrary value right now in order to incentivize people to eat. Yeah, but you do realize if you use value-based goals, there's a problem, right? Let's say if I say eat burger, you get +2 reward. What if agent keeps eating burger, right? You do know that in a human, if you keep doing something, even if something is very positive, like eat a burger, eat ice cream, you won't want to do it all the time. But these AI agents, they will just keep eating the burger because the reward is always going to be 2. So this needs to be changed, and, like, some people have changed this reward to say that you only get a reward if you're hungry. Okay, so, and more you see that this reward kind of converges to internal motivation. Like, if let's say you are satisfied with food, you won't want it anymore. So that's something that I think reinforcement learning, the traditional one, doesn't really cater. And we need to find out more about this in order to decide what kind of goals that we can set. Now I'm going to leave it as that because I don't have an answer to how to generate goals. So that's an open question for me as well. Comments?
So goals should be imaginable. Are you saying that imaginable means that it can express in language, it can express in forms? Next question is that imaginable by one agent, or in a multi-agent situation, imaginable by multiple agents? So these are my 2 questions.
I think as long as one agent can imagine it, it can be a goal already. Natural language, whether it can express or not, is easier if it can be expressed in natural language, but it may not need to be. Like, for example, if your goal is to eat something, okay, yes, you can express in language, I want to eat something, but you can also execute the goal without doing the language. In the past, humans don't have language, right? Or rather, animals may not have language in the past, but they can still eat, right? So that kind of goal, you need not have to have natural language. It's just that if we have natural language way of expressing a goal, you can communicate better to a population, and then you can have group goals and so on, which in some sense is helping progress, because if everyone works towards a common goal, you can chip in different expertise together, and it might do more than just what a single person can. Like right now, we have open LLMs, large language models. If like you only have one person doing it, you may not go too far. But you have a lot of people doing it. People can chip in different expertise. Some can do software, some can do hardware, and so on, and you can get the product out. Yeah. So I do think natural language is useful as a goal for social purposes, but it's not necessary for a goal to be executed.
Yeah, I agree. I agree. But if you don't express it in language, how is it going to be computational here in the memory soup, right? So if your goal is only you know when you reach your goal by your own experience, then it's not going to be computational, right?
So there's two different things. I think I can go to the next slide since we are talking about language. So all right, so I talked a little bit about the proximity just now, like multiple actions can be aggregated at higher levels by a proximity graph. Yeah, so at the top level, you have a very high distance. At the lower level, you have lesser and lesser distance. So this is hierarchical, navigable small wolves. Yeah, how they did this is actually a bit different from what I'm talking about just now. How they did this is some probability, and then like you start from the bottom layer and you drop a certain node with a certain probability as you go up. So at the top, you have more and more sparse connections. Yeah, what I'm thinking of is more like if you have a cluster of nodes here together, this could be like one layer, and then you can, based on some clustering constant, you can get a cluster of nodes here. So it will be based on clustering. Yeah. So haven't thought fully about how to get this, but the idea is the same. At the top levels, you have longer distances. At the bottom levels, you have smaller distances. Yeah. And then you can, like, if you want to find your way through, you can just do pattern matching to find out like where is closest to the goal. You just do a greedy match. You could also do a tree of thoughts kind of thing. Like you could have a tree of actions you take, and then you see at the end of like maybe 20 look ahead steps who gets the closest, and that could be it. Yeah. So yeah, that's one way of doing it. Can goals be formed by natural language? So that's one thing that I would like to ask also, because people have tried to do LLM-based agents, and like Meta GPT, Auto GPT, you try to give a broad goal, and then you try to get the sub goals out. And what we find out is that for goals that are more like amenable to structure, like for example, if you want to say, I want to create a game of maybe Pong, then our sub goal could be like get a Python environment, get assets, use assets in game. Yeah, so this is like something like chat dev also did something like that. So if let's say your goals could be split into like parts, and in this case a sequential step, okay, you could actually write your goals in natural language and get it to like at each step, then you express out like what are the substats needed and eventually the code. So at each step you could call some API or code or like image generator, and yeah, eventually this is your meta goal, this is your main goal, and all this here will be your sub goals. Okay, and the sub goals over here are not generated by like let's think step by step kind. These are given sequential goals. Okay, so one limitation with Auto GPT is that we don't really have the sequential goals, you see. So if you just say let's think step by step, sometimes the goals that you get, may not exactly reflect like what is needed. Like it may be all over the place. Like the last goal might give you back something that you need to do again. Yeah, you can end up in loops like that. Yeah, so I do think that in order to get goals in natural language, what would likely need to happen is that you need to have a way to make it such that your sub goals should always be of a smaller magnitude than your main goal. Yeah. So if you have a way to constrain this, okay, like in a sequential way, you can do that because like every step is a smaller magnitude. If you have a way to do this, I think it's possible to form goals in natural language. You can store all these transitions in your memory. Like for example, create Pong game to get Python environment. Yeah. So all this list of steps can be stored in memory. And you can store both the macro memory. So this will be the macro memory. And you can also store the micro memory. And what's the micro memory? The micro memory will be like pip install Python and so on. Sorry, pip is Python, sorry. Maybe pip install Pygame, yeah, that kind of stuff. And create a player class and so on. So you could have all this stuff, both the macro and the micro stored in the same memory. And based on the memory soup idea, when you want to refer to memory to get what to do for each step. So each step here could have different memories that you can get. Like you use different memories to condition generation. At each step of extraction, you can extract from the entire memory soup. And this is very important because right now we only do everything by like paragraph chunks or passage chunks or single sentence. You know, I do think we need to embed everything at different layers, paragraph layer, sentence layer, passage layer, all in the same soup. And then you just extract what is the most relevant by maybe embedding similarity. So yeah, it's did that answer the question? Yeah.
Yeah. Yep. Very good.
Yeah, so I quite like this idea. I think this is applicable for a lot of systems, not just fast and slow. But I would say that how this natural language relates to fast and slow is that maybe at the higher levels, it is natural language. And once it reaches a certain point of time, it will become motor actions or like move to square A, square B. So like navigation is one subset of like what could be done. There could be other ways. And then at the most macro level, you know, you might think in terms of language. So I do think somewhere up, let me just write this down somewhere. Somewhere up the line is natural language. And then like over here will be specific actions. Yeah, so as you go down, you from natural language plans, you go down to the action plans. And I think something like that will get us very close to fast adaptable agents that can do almost anything. Because at the bottom, you can get the specific actions.
Hey, John, just a wild speculation. I remember I watched you one of these Zoom calls with symbolic AI.
Yeah.
So some actions, some goals can actually be represented by symbolic symbols.
Yes.
You think?
Mm-hmm. So I don't constrain goals to just be natural language. You can also have symbols. Just yesterday, I was talking to Satoru, another person who presented at ICDL. He also says that his macro goals are like in terms of symbols, and you can do some symbol manipulation at the top layer. Sure, if you can abstract out into symbols for your top level goals and you can mix and match, I think it's just a way of representation. Natural language is just one way of representing it. Yeah, if you can convert it to symbols, sure. I mean, people can convey ideas in math as well. That's okay. You can call it a language, but that's also symbol manipulation. So if let's say you can express your goal in a specific form, and that form is something that is quite precise and like something that you can do your search over, I think that's fine. That's just a different abstraction space. So I'm not discounting that could be other.
Yeah, what I'm thinking is like, you know, if you have like, you know, something really similar, like, you know, pattern matching in English, in German, in like, you know, one of the, you know, native Indian languages, we can represent that with a common symbol, right?
Mm-hmm.
And that will help this whole memory soup to be multilingual and transparent in different situations and different culture, different languages.
Yeah, possible.
I think to that end, I was going with a similar sort of, again, I'm playing with implementation in my mind around what the data structure of a memory soup look like. The idea that there's many kinds of embeddings which all have to play at the same time. Right? So the soup becomes an index of indexes, right? If you consider one embedding type to be one index. And then one of the things that would be interesting is you get this Rosetta Stone effect where you have a picture with a description as part of the learning set. And so it embeds up in the embedding for images as well as in the embeddings for text.
Nice. I like these ideas. So different embedding space gives rise to different parts of the memory like this. Like you have location, visual, audio, all these are actually same part of memory, but you know, encoded in different chunks. So I think what you're talking about is you have different indices for different, like this is for location, maybe this for visual, and you can like learn this concurrently. And basically when you want to search your memory, you can block out certain portions and you search only those that you are interested in.
Well, or perhaps, if you have we're talking about abstractions and goals, right? So if you have a location, but you want to imagine what it looks like, you say, this is location index 26 or whatever it is, right? It's going to be a high dimensional vector of some sort. But I'm looking for the closest approximation in visual terms.
Yes.
And it goes, right, if that makes sense. So then you can go, well, my closest approximation is this thing I once saw, which may also have a location associated with it. But something along those lines. If you see what I'm getting at, the idea is they all become sparse for any given memory. Right? You don't always have audio and text together or visual and location together.
You might have it as XX, like basically you have no input. That's possible also. So yeah.
And so I was thinking about using a database because that's just my background. But then it becomes, in a database sense, relational database, it becomes trivial to do that. You just have a series of indexes. You can keep adding new ones. The real question is, what do you make the golden key? My best guess is a timestamp plus whichever one you prefer, whatever you've got handy, right? Because it's actually completely arbitrary. But that becomes your key from this memory to this representation of that memory to that representation of that memory. And the only thing I can come up with is time as the universal.
Okay, I didn't put the time here because actually in our memories we suck at
we do. No, notice I'm not really searching by time. It's just a reference. It's just
but there's nothing in AI systems that prevent us from putting time as an index, because I do think having time makes it much better in terms of planning. So we actually are a very poor gauge of time. We have a very poor gauge of time, and that affects our planning. That's why we have AI systems to help us plan our daily routine. So I do think in AI systems, there's no need to constrain ourselves to think like a human. We can put in the time vector in the memory, no problem. Okay, so let's go back to the slide. I think I will need about 15 minutes, so just bear with me I think let's complete this today. All right, so the next thing I would like to talk about is memory soup, as what we've been saying. Like different levels of abstractions, okay, would all go to the same memory soup. And this is similar to like the 1,000 brains theory. You have different models of the world. And actually all of these models of the world could all be like from the same modality. It could have different abstraction spaces. Like one is the object, one is the pixel level, one is the scene level. And in the end, all of this will help to make a decision at the end by voting. So the abstraction could be hierarchical, it could be parallel. All right, hierarchical just builds on previous representations. Okay, like what you saw just now with the hierarchical prediction, your top layer could be the more and more abstract ones because it builds on the transitions of the bottom ones. Okay, so how do we do pattern matching to the right level of abstraction? This one, you just need to find based on your entire memory soup. Okay, in your memory soup, you could have different transitions, like here to here, you could have here to here. So as long as your end state here is directly like the closest to your goal, I think you just pick the transition that gets you closest to the goal, like after you apply this transition here. Okay, of course, like how do you know whether this start state here correlates to your start state? Because it may not be exact match. Again, there could be some similarity score. So it's a bit fuzzy here, because if we don't do exact match, sometimes we may get the wrong action. Because like in a grid world, you go one square up or one square down, you may get it wrongly. So this pattern matching has limitations. And yeah, I mean, of course, when we navigate, that's why we may not navigate properly most of the time. We might need a GPS. Like this pattern matching is great for like tasks that have like huge room for failure. Like it's not exact kind of task. You can have leeway for error. Okay, so I do think if we do this kind of memory soup thing, it's probably for this kind of task with a high margin for error, because you need to do this kind of fuzzy matching in order to match the memory soup. There's no way you can get exact match in a high dimensional world. There's no way. It's just too many states to store. All right. So one thing that I have for this memory soup is that, all these different modalities like vision, sensory stuff. I mean, yes, they could all form part of the same memory soup, but you know, when you retrieve memories, you only retrieve based on that modality alone. So when you store the memory, you can store everything together, visual, audio, and so on. But if you are in the visual pathway here, you are this particular agent here, you are only allowed to retrieve based on what you see. So if you see only vision, you know, you shouldn't retrieve stuff based on touch because you have no information at all. You only retrieve what you have information on. So while the memory soup can contain everything, but different modalities, in fact, in the same modality, you could have embedding space 1, embedding space 2, and so on, based on like the structure. And like, how do we learn these embedding spaces? I'll touch on the next slide. You could have different embedding spaces, but you only retrieve those embedding spaces that you have information of. Makes sense, right? You don't retrieve what you don't know. You only retrieve based on what matches you. So you are the particular agent right now. You say that, yes, hey, the cup is warm. So you try to retrieve all the memories of warm stuff. Do you retrieve stuff that is sharp objects? No, you are not the sharp and a smooth object agent. But if you are the sharp and the smooth object agent, you will like, this object is sharp. Let's retrieve all the objects with sharp in it. So in the end, everyone will come up with a different representation, and then there will be some consolidation at the end, maybe like go by majority matching to see what kind of object fits all this criteria or most of this criteria. So yeah, this is the kind of idea that I'm thinking of for memory soup. Your retrieval is conditional on your inputs, but your storage is everything. Like every single agent has access to everything. It's just that when you retrieve, you block out certain parts that you don't have information of. Yeah, so this is very similar to like different kind of memories with different types of abstractions. You store it all in the same thing. You can just retrieve. This whole thing is your soup, which you can retrieve, and it's a selective retrieval based on the kind of state that you are in or your kind of inputs that you have. Questions on memory soup? Yeah, I think this is a great discussion. I do think there's quite a lot of clarity here. So how do we get the different embedding spaces? Is actually, I think, based on inputs and structure. So these are all self-supervised. So like, for example, you're talking about this agent here. So let's say this is the object agent. Or like maybe you can call this like maybe the edge agent. So it's like to detect like straight lines or curve or not straight lines. Yeah. So okay, yes, this might be like simple features and so on, but it can also be a decent embedding space because this is a full view of the object in terms of the agent's perspective. The agent only cares whether it's straight or non-straight lines. That's the only visual view that is given. And based on this, okay, it means that you will store information based on like whether the thing is straight or not straight based on like the input stimuli. And you can actually learn based on self-supervised learning based on like after you've seen the image, then you say that, hey, actually yes, it's a straight line, hey, it's not a straight line. And okay, how do I put it? Maybe it's not an edge agent. We shouldn't call it edge agent because this is very similar to this. Just think of another way. Maybe agent one that looks at a certain perspective. Yeah, I won't even say the perspective because I don't even think like there's an edge agent inside. Okay, I mean,
could it be optimized for a skill?
I also don't think so because like if not, how do you know the skills beforehand?
Oh no, I didn't say that. Right? I got no idea how you do that. Right? But in terms of to describe it, instead of just it looks at things from a certain perspective. But say if you take the edge detection, its skill is detecting edges, right? So the challenge becomes to constrain it to a particular capability. That's why, or skill or something. I'm just trying to figure out the right word there.
Right. So actually, there are certain action spaces that are given directly based on this agent itself. If the agent is an eye, the action space maybe there's the circuit for the eye. And this state 1, state 2 is the environment state 1 and state 2. But in the agent's perspective, the agent can be, let's call it SA1. Okay, maybe not SA1, maybe like state, I don't know, state to the agent itself. So maybe state internal 1 to action internal 1 and state internal 2. So from state 1 to state internal 1, there is some form of mapping into abstraction space. And this abstraction space here, I honestly don't know whether is it learned from birth or is it like we just have a neural network and then it just learns to fit the abstraction space by itself. But the idea is because of the way this abstraction space is, it pays attention to different parts of the input and it learns different things. And so this abstraction space here is more like your embedding. So maybe your embedding is learned. So it's like you have flexible ways to map your state to this embedding space, and then you have flexible ways to map your action to an embedding space as well. And then if you have enough mappings, hopefully one of them is an age detection, hopefully one of them is something else. You may not define it at all at birth. You just make it flexible, like 1,000 different decision-making agents. I throw you in the environment and you just learn what you need to learn. Yeah, so that's also why, like people with eyes that are not functional from birth, like for cats, they sew the eyes shut. And then after a while, they let the eyes open again. The eyes are both fully functional, but because they see no input at all, the cats become blind for life. So it could be that because in the earlier parts, these abstraction spaces for vision are not learned. And then once you open your eyes again, it cannot match anymore because like the rest of the connections are so strong. Your visual inputs just get ignored. Yeah, so this is a way of learning, I think. You just have flexible mapping spaces and you just wish the agent luck that the agent learns something useful. Yeah, so I do think it's something like that. And how we learn the embedding space might be just predicting the next state. So as long as you can predict this next state well, you can learn your embedding space well. And then because you can do self-supervised learning for any kind of abstraction space, you will learn different kinds of things. And one of them could jolly well be an age detection agent. So I go back to the age detection point. You might still have an age detection agent, but it's not explicit. It's just learn because you want to predict the next state well in this abstraction space. And this embedding space just works. Questions on this? I think this is a bit hard to digest, but yeah, this is I think quite a landmark idea, I think.
I think, well, for one, so if you take the unfortunate cats as an example, right? So it strikes me that when is the right time to learn to see is a genetic feature of the cat. Right? So it's handed to the cat in its underlying structure. It's not necessarily explicit in the genes, but it becomes an implicit feature of expressing those genes. Right? When your eyes open, you are in a state where learning vision is a thing you can do relatively effectively. But if you miss that window, as you say, maybe the stimulus is too weak to act on it. So I think there's something about this intrinsic structure of the creature where even if it's not explicit, it is effective. Does that make sense?
Yeah.
And
so
with an AI, we don't even have that.
Yeah. Maybe what we need to do is just give it the right input space and right experiences, and it can learn stuff. Like you see, if let's say I give you your eyes, but I put you in a black room, eventually you will learn to ignore your eyes because it gives you no useful information at all. So not just the structure of your body, but your environment experiences must guide you to learn the right abstraction spaces or embedding spaces. And all these will store in the different indices of the memory. So all the different embedding spaces will be part of your memory. And you just retrieve according to the agent itself. Yeah. And one other thing is like, why do we think language is so common? Like it gives you the same kind of representations in general across different populations of humans, like in different parts of the world. One reason is maybe the Earth is more or less similar. I mean, we experience like similar seasons. I mean, some of us may not see snow. That's why we don't only know one word snow. Eskimos know about hundreds or thousands of words for snow. Yeah, so in terms of like language and like why are we all the same when everything could be so flexible in the brain? It could be jolly well we have the same features, same structure of the body, and generally similar experiences. I mean, we can differ, but also not much. But it could be very well that a human population living on on Mars or some, let's say you have a population living on the satellites. Okay, no human interaction, nothing much. You interact only the AI or maybe some small group. The experiences might be very different. So that human may not know what's grass, may not know what's land, and so it's living in the satellite for so long. So it kind of thinks that it learns. Maybe when it goes to Earth, you'll be very surprised with grass. It's like, hey, what's this? What's this color? I never seen before. Yeah, this could happen. Of course, we don't have the experiment for this because I think it's quite unethical to lock people up somewhere and not expose them to stuff. Like there's a philosophical argument about like Mary not seeing the color red in her life, or living in a black and white room, never seeing color, whether the experience of color will be like new if she just reads about color but doesn't experience it. I think if you don't experience color and you for a good portion of your early life, you may not be able to decipher it later on. Yeah, just like how your eyes get shut. Yeah, we just don't have the way to perform this kind of experiments, but maybe they can do it in rats or in cats. Yeah, I do think that like past a certain age, you may not be able to change these features anymore. Like these abstraction spaces might be unchanging after a certain time. Yeah, because it makes sense. Because if you keep changing your abstraction space, imagine your memory, right? Your memory will keep changing, because the way you encode this will be different. Yeah. And then when you change your encoding spaces, maybe the way you do prediction will be different also. So after a certain point in life, your abstraction spaces need to be fixed. Okay? If not, you cannot learn memories reliably. Does this make sense to you? Because if your abstraction spaces are changing, what you store in your memory will need to be updated again, right? And even the action prediction might change as well. Yeah. So I think this is one thing that we need to take into account, and that is also why probably after a certain amount of time in life, if you don't get exposed to a certain stimuli or certain experience, you may never learn it anymore. Yeah, I'm actually done with this slide. Any questions on this? Okay, let's just move on because I think it's quite late. I'll try to end in 5 minutes. So the next part is actually on emotions. Sorry, is there anything? So emotions is that like instead of just forgetting memories, we can just imbue the new memories with a certain higher preference score based on certain emotions we have. So we can go by similarity, then by emotions. So this is one way that we can imbue stuff. All right, emotions like fear, happiness. Okay, we might prefer it more. Sadness, avoid it. So I've been toying with this idea of whether we can just have only one system for emotion. I think it's not possible. Okay, we probably will have a fear and desire circuit. Why? Okay, because if we talk about fear, right? Fear is to help us avoid dangers. Okay, but if we just do a desire circuit, okay, you will just pick stuff with higher pleasure, desire value, or something like that. You choose the action spaces that give you something happier. Okay, you may actually not be too sensitive to this kind of fear thing. You might like say that, hey, this memory is actually quite good. Let me just pick it up. Let me just do it. But because you don't, because fear will always be at the lower ends, you see. Sometimes if you don't like if you don't store this separately, you may not constrain your action space. So if you have a fear circuit that is learned separately, or not really learned, but I think fear is like inbuilt. You don't really get to choose what you fear, right? So you can constrain your action spaces so that you don't die that easily. Okay, like there's some cases where like some babies have no sense of pain. All right, it's very likely they'll injure themselves very easily in early life and they need extra supervision. So if we don't have this fear network, okay, we may not live long enough. All right, so I think this fear network, although it's like the amygdala and so on, is very rudimentary, but it helps with survival. Okay, if we don't have this, if we just purely based on desire, you might do stuff that injure yourself for pleasure. Yeah, some people are like that. But if you have the fear circuit, at least this prevents you from doing things like this. So any comments on this? I do think emotions, you can select different pathways, like for example, state 1, state 2, action 1, state 2. This could be a happiness value of 5. And then like state 1, action 2, state 3, action 1, state 2. This one could be a happiness value of 10. Okay, let's say we have 2 different things. Although technically we want to choose the shorter action, but maybe you take a walk around the park versus you run around the park. Maybe you take a walk, you feel happier. So you might do the walk instead. So you might prioritize like even inefficient actions sometimes because it's more pleasurable. And this way of emotions thing might actually help us to prioritize like what memories are useful, what memories are not. Like, because if not everything in your life is all going to be encoded in memory, this will decide, emotions will decide how strong the memory is. Yeah. Any questions or comments on this?
I think that the challenge is how where do these emotions largely come from? So I'm going to ignore people who have had awful and bizarre experiences and just go for right down the middle, right? And if we stick to that path for a minute, then we find a really high level of consistency around these things, right? There's plenty of exceptions to the rule, but the central path is actually quite narrow, right? People enjoy eating fatty, sugary food until they feel unwell. They enjoy conversing with their friends until their friends irritate them. But there's actually a surprisingly narrow path, and I think this is sort of talking about this is where I think there's this inbuilt structure we don't have for AI. Right? As people, we have genes and society to keep us on this relatively narrow path with mixed success, because variation makes us as a species more survivable. But this remains this relatively narrow path. And so I guess that the challenge for me is to highlight we don't have those facilities in AI. We don't even approach them at the moment. And so without them, we are going to find these structures very difficult to build. We can either ape humans, for a better term, and go, we'll make an LLM that acts like a person because it's trained on human language, or what, right? I don't really know what the what is, right? But we see large language models have human-like responses. Well, duh, because that's all they know is human-like responses for the most part. It's now changing a little bit.
I mean, because the training set is human data, right?
Exactly, right? So do we want them to act like people, but if it's an AGI, like if it is generally intelligent, then that's actually kind of troubling, because people are pretty worrying a lot of the time. There are a lot of good features of people and some pretty bad ones too. And they don't have, an AGI doesn't have the same risks that humans do, right? They're not limited by things like dying, right? They have other risks, but that's not one of them, right? And so and emotions, I think, are part of the underlying structure, is my suggestion, right? As you suggest aging, but aging, emotion, genetic expression and implicit behaviors and all the rest of it. But they don't have that structure isn't apparent to me, at least in AI.
Yeah, so Rich, I think you're absolutely right. I was about to ask this question, right? So emotions, there's a whole school of life-based philosophy. If you go to Taiwan, and many universities, I mean, they have been studying and researching about life sciences and life philosophy, right? And for them, emotion is an inherent given part of human spirit. And you cannot have, like, animals don't have the full spectrum of emotions, and human emotions is really a sign of, to them, a sign of divinity, right? So I think what we have here is very similar to NVIDIA's audio to face, where you can artificially create an emotional expression by facial muscle movement, using AI to detect the emotion from audio clips, right? So I think my suggestion will be, say, this is like human emotion representation or artificial emotions, and sort of set a separation between the real human emotions, because that's a big field that connects to consciousness that I don't think we're ready to deal with.
Yeah, I mean, we can talk about consciousness another time. That's not the focus for today. But my rough take on consciousness is just the upper layers of decision making. I do think a lot of decisions happen outside of consciousness, and that's also very important. I mean, if you ask me whether we have free will, my answer is no. Consciousness is just a way of processing. Yeah, but let's talk about that another time, because I still have some stuff to talk about. But emotions, I think, are necessary, because if not, we have just have too much memories to pay attention to. It may be inefficient, as what I showed here. Like, you might choose some longer path. Okay, but in general, it helps us. Okay, whether or not we can learn emotions or not, please chat with me like off the session as well, because my rough take right now is that it's inbuilt. Like, it's just given to us as our genes or so on. Yeah, I don't think we actually learn emotions. We might learn how to manage them, but emotions happen outside of our control. And I don't even think it's learned by life experience. It's just like you have a certain fundamental heuristic, and if it matches, you trigger that emotion. Yeah, like if you get isolated from a group, you feel sad. If you get what you want, you feel happy. I mean, even my kid expresses emotions even without me telling him to. He wins a game, he feels happy. He loses, he feels very upset, and that's very natural, right? Across many kids. So yeah, I had to leave this slide as that. I think this emotion fusing with memory is very important for learning, because emotions can also guide us to learn. Like surprisal memories, you will learn the new memory more. It will be encoded more strongly. Like, so yep, let's leave it as that. 1 minute, I'm just going to say that I think intelligence is not just a single agent, but with many agents. Different agents imbued with different memories will lead to different actions with the same situation, and this will lead to diversity in exploration. So we get diversity in exploration not from the individual level only, we get it from the population level. Why? Because as you know, in the learning fast and slow, if your memory has a trajectory, you end up doing the same action all the time, which is what happens to most people. We end up being stuck in certain habits. We walk the same path. We use the towel the same way after we bathe. How then do we get diversity when the environment changes? It's through multiple agents. When the environment changes, some people adapt better than others, and these people might go on to reproduce and so on. And so this leads to a population level adaptiveness. I don't think adaptiveness happens at the individual level. All right. So what kind of memory should we share? So I had this discussion. I think some of y'all were there also for the Machine Learning Street Talk book club. So we may not want to share all the memories, because as we talked about, like backflip and so on, if I share memories of backflip to everyone, what if you don't have the capability to do it and you injure yourself? So you may not want any person to share memories, but maybe the best agent should transfer memory to the rest only, so that the rest can learn. And this memory must be relevant for other agents. So if you don't think it's necessary, you shouldn't learn that memory. Okay, because you make your decisions based on what memory you have. If you take in memories from other people, you might start to act more and more like them, which is not desirable. Okay, we don't want everyone to have a hive mind. All right, hive mind leads to everyone doing the same action, and that's not desirable. We want people to have diverse actions, and that's why when we choose what memories to take from others, I think it must be related to what you want to do. It must be relevant to what an agent wants to do, and the agent might be able to draw memory from the rest. I would treat this more like a curriculum learning thing. Like, for example, let's say if you want to learn about LLMs, then you just find resources relevant to your use case. Okay, do you want to learn the entire encyclopedia of what everyone is doing LLMs? like all the millions of research papers on large language models? Anyone? Would you want to flood your brain with all details of large language models? Who says yes?
For a limited period, yeah, sure.
Okay, because maybe large language models are relevant to you. Okay, but who says no? Who? That means the good and bad, everything, all the memories of large language models flood your brain right now, and you know everything. Who wants that? Yes, raise your hand. Who thinks that's a great thing? Okay, who thinks no? Okay, there's no response. So okay, so there's no. All right. So Nancy, you raised no. You want to explain why you think it's not good to flood your brain with everything?
Right. Hello, yeah, this is Nancy here. So yeah, we don't want all the information in our head, right? Because then we'll go mad if all the information comes in our head, and it's like too much information is also not good for taking decisions and all, right? So
Yeah, correct. So that's my point. Thanks. So I do think that too much information is bad actually. So only like agents with the same kind of life goals or environment should share information with one another. Like, I wouldn't want to know information of how a bat flies. Okay, because it's just irrelevant to me. I cannot fly, you see. So unless I could suddenly grow wings and fly, then I want to get information from the birds how they fly. If not, it doesn't make sense for me to know how they do it. Maybe for curiosity and so on, but it doesn't really affect like how I live my life. Unless knowing how they fly, I can catch them better to eat them. Yeah, then maybe yes. Okay. So yeah, then there's this idea that I have also about local proximity memory transfer is that because people in the same environment likely are closer to one another in distance. So if I want to get information about like maybe what should I eat for lunch today, I'm not going to ask. I'm in Singapore right now. I'm not going to ask someone in UK, hey, what should I eat today? Because the environment is different. Like they maybe tell me, oh, you should eat fish and chips or something. But the fish and chips there and the fish and chips here in Singapore might be different. So we might only want to take information from people around us. Like you might want to ask people living in the same block as you or same area as you, hey, what's good? Then they will know, oh, there's this store nearby, it's not bad. Yeah, you wouldn't want to know like every single food store in the world. That's just too much. So local proximity, I think, is great. So in the artificial systems that we create, I also think that some form of sharing is useful, but we shouldn't share too much because then everyone will do the same thing and then we won't get diversity. So the main thing to summarize is that you should share only if the agent thinks it's relevant, and also if it's local proximity, there's local proximity, so that the information is relevant. Okay, so what about search systems, right? You talk about Google, they have all the information in the world. How's that? All right. Yeah, I mean, they don't really need to make decisions, you see. They're just there to provide the database. So you might be asking, hey, why can't we just provide each agent with database of every single thing? Sure, we can do that. But when the kind of environment changes a bit, everyone with the same database might make the same decision. That's not good. So because Google search, you don't have to make decisions, you see. It's us that look at the information that make a decision. And we have prior memories and so on. So we may not want to, be like a huge database to condition our actions. We may not want to have that. Because as what I said earlier, everyone will do the same things. So yeah, I think there must be some guidelines as to when to transfer memory. And memory could be of different forms. In fact, it might not even be possible to transfer memory exactly. That's why we have language to transfer to one another. But for AI agents, if let's say we could find the same embedding space, constrain everyone with the same embedding space, we might be able to transfer memories not just at the language level, but at embedding level. So it might be possible to do that. Okay, so this is for AI agents. And you may also be able to transfer the reflections or longer term reflections. So this we can do as humans as well. So reflections could be like, Antarctica is dangerous. Okay, and this is because of 10 years of experience avoiding ice cap meltdowns and so on. So you might be able to, yeah, I'm sorry for the people living there. I have no idea whether it's dangerous or not. I'm just giving an example. Or maybe I just say like why it's dangerous. Okay,
Oh,
so
no, apparently it is really dangerous. Yeah. Like
okay. All right. So you can consolidate this thing into one phrase like that, and you might be able to share this memory so that you don't overflood the other agents with all your specific experiences. Like the agent may not be going there to Antarctica or to countrywide. You might just need to transfer this knowledge and it's enough. You don't overwhelm the capacity of the individual experiences. If not, the agent might start to live life avoiding ice caps or avoiding wet surfaces and so on when there's no need to. Okay, so we might be able to transfer these reflections as well. And we might be able to transfer meta memory, which is like like higher level memories, like maybe like language level and so on. So I have not thought of a way to transfer this properly. I mean, I think this is a huge level of huge work that we can do research on. There's a lot of possibilities, but one thing for sure is you shouldn't transfer everything. Yeah, and likely is the best agent should transfer, and only for relevance, only transfer relevant stuff. Comments or questions?
So how do you basically plan to transfer this meta memory?
It's just a simpler copy and paste because AI systems it is in the same embedding space, which you can make it
Okay.
so you can just
Hmm.
plug and play. Yeah.
Oh,
For
okay.
humans, you might need to do in language. AI can also transfer by language as well. The meta memory might be language, or the reflection might be in language. You can just put that as one of the items in the database.
Okay.
Yeah.
Okay,
So
thanks.
it would be interesting, depending on how that was structured. So if we were talking about, mentioned earlier, this idea of explicit linkage versus nearness or some other metric, right? If it was explicit and you transplanted the memory or an idea or whatever you're going to call it, then there'd be nothing to link it to necessarily. Right? So it might just sit in space and atrophy and die, right? But if it was based on proximity, then it would work better. But on the other hand, proximity is just a lot harder to work with because there's a lot more work to find things.
Correct. That's why I quite like the implementation in this thing called generative agents and interactive simulacra. Is the for those who don't know, is the sandbox environment where they simulated 25 agents in a town, and then like one of the agents want to host a Valentine party, and then they go and talk to one another and they spread information in local.
That was a great paper. Like I loved it. And one of the things that I had in there that was really great was you talk about emotion earlier. Was they talk about essentially they don't call it emotion, they call it significance of memories. So each of the agents, to make them more scalable, edits out their own memory. So they just forget stuff that's tedious.
Right. So actually, I like a lot of things in that paper. In fact, I think that's the best paper of the year, if you ask me. It's the most relevant to my research as well. They modeled memory quite well. And I think in this case, like you transfer memory also in terms of local proximity. Right now, yes, we can transfer memories outside of our local proximity. We have WhatsApp, Telegram, Meta, Facebook, Instagram, LinkedIn. You have different ways of social media outlets, and you can transfer memory globally. Okay, but is it necessarily good? You look at case studies of people using social media. In the end, they compare too much with other people. They become depressed, and stuff like that could also highlight that maybe you don't want to learn from experiences from everyone. Because not everyone is doing the same thing. If you are a superstar, you have different. You meet with prominent people, then you start to think, hey, how come I'm not meeting prominent people and so on? You may not need that in your life. Yeah. So while in actual life we start to have more and more global memory sharing, you start to think in your own life also, like, is it necessarily good? Just think about that. I'm just gonna leave it as that because I don't think it's 100% good. It may be useful, but it may not be great. Okay, you might still should only share information within the groups of people that are similar to what you want to do. Like I like to create fast and adaptable agents, so we should share memory amongst people who want to do that as well. Okay, rather than people who like say, oh, AI is going to destroy the world. Maybe we don't want to talk too much about that because that's not very relevant to the purpose. So I think global communities might make this local proximity a little different. This local proximity might be proximity by interest. Yeah, so we might not be geographically similar, but it could be interest groups. So yeah, just some thoughts. Okay, let's move to the last slide. Okay, this one I've touched about just now. Different embedding spaces could be stored with different indices, and then you just extract out stuff that are relevant. You know, in fact, if let's say you want to compare this for location, visual, audio, sensory, motor, you might also want to do it by blocking certain things. Like you might want to just do location first. Then you take out like maybe this key. Then you do visual. Then you take out another few memories. Then you do by audio. Okay, this case is everything is going to be key one, but you know, you could, let's suppose that this is 0, 0 and this is 1, 1, 1, 0. You could take out this one here. So you could do by like some kind of random forest matching where you block out certain modalities and then you extract out the data so that you can be a bit more robust to noise because maybe you encode it wrongly. So because of that, when you do your consolidation later on, you have more candidates to compare to, you might find a better answer. So random forest like search to block out certain subparts and like do cosine similarity only on a subpart. So let's say this is a subpart. You could have subpart 1, subpart 2, subpart 3, and so on. Based on like maybe subpart 1 is like that. Let me just draw for you. Subpart 1 is like this. And then subpart 2 could be like this. So you could have different subparts here and you extract out different memories and make it more robust to noise. Yeah, that's random forest. Random forest quite robust to noise because they do basically they only select certain components of your original data to process for each forest, and then you consolidate them together through majority voting or some form of consolidation. So I do think this is very useful. So this will be the future when we can store all kinds of modality in the same memory. And this also allows for memory soup where we can store different levels of abstraction all in the same memory. Okay, Kyron asks, are there platforms or tools to use to store all these multimodal things in memory soup? Is it a database? It can be huge to index in a live situation. Yeah, right. I think this will just be different line items in one database. There's no index because you don't have index anyway. You can index any of the subparts, like any of the like location or visual audio can all be an index. So we don't have to store it by any index. We can just store it as one chunk of like as one vector.
Conversely, it can be lots of indexes in one database. So there's lots of approaches to this, I think. And like, could it be a database? Yeah. The problem at the moment is that the databases aren't fast enough. So the reason why transformers are preferred for that processing role is because they're more efficient than what came before them. And at the moment, the way that the systems work, efficiency is an issue. And so, I mean, if you scaled up, like say, for how fast your memory works into a current system where you were indexing location visual, like 18 different types of stimulus simultaneously, then tried to wedge that into one database, you'd be hard pressed. It doesn't mean it won't be one searchable environment, right? That's a different conversation. But if anything, the cloud architectures have shown us that you can make essentially, or actually HTTP and the REST architecture have demonstrated you can make one searchable index of everything, right? That's essentially what the World Wide Web is, what HTTP sort of addresses are all about. Oh, URLs, that's the one I'm looking for. So in terms of how do you store it, like with the internet, with the web, that's kind of somebody else's problem. The real trick is figuring out how to find it. So, and yeah, you've sort of mentioned Pinecone. I asked, I didn't get any response to my aged nerds that I know on LinkedIn. And I asked if anyone can tell me why I wouldn't use, for example, a relational database. I cited Postgres, but could be anything. Why I wouldn't use that instead of Pinecone or something like it, a vector DB. and that remains outstanding. I got a half an answer from the Neo4j guys about graph databases, but it was their argument came down to efficiency, essentially, and doing aggregate queries on graphs is not efficient if you don't have a graph database. Fair enough. But what do we do for everything else? It wasn't clear. So I haven't yet found the killer app for vector databases. They're very much very cool at the moment. Yep. If you're looking for VC funding, it's a good place to be. But that doesn't make it necessarily very useful at the moment compared to what you might term legacy structures systems.
Yeah, actually, that's a good point. Right now, our thinking is very constrained in our current architecture systems. Like we are thinking databases and so on. Maybe, this part, as long as you can store all this into one soup, if you put in a database or not database, it could just be multiple parallel agents calling one another. The location called the visual called the audio and so on. It could be like multiple chains of databases and so on. It need not even be the same database. I leave it open because honestly, the structure here, we don't know yet. All right. But the idea is you, from one input stimuli, like for example, if I see an image of maybe like a school, I start to remember my episodes of memories in the school, like the songs I heard and so on. You can trigger different parts of the different state space or different semantic spaces, memory spaces and so on. It need not be just one line of embedding vector like that. It could just be like different agents talking to one another and asking, hey, I have this, do you have any match, and so on. Yeah. So yeah. To be honest, I don't have the answer for this, but this is like the most straightforward for me. It may not be like that. So I would like to caution, like, database is the only answer. No, that's not the answer. Yeah. The actual system may not even be a database. It just be multiple agents talking to one another. And then it appears to be like a database outside, but internally it may not be. Yeah, so hopefully this clarifies stuff. Okay, yeah, thanks for staying through. Actually, I have one last slide here. I just want to, like, maybe we can end here just to pick your brains a bit. Can intelligence just be a graph traversal problem or like a distance problem, traveling salesman problem? So I like to say yes, in some sense, yes. You can map your intelligence task into a search space, okay, with certain states in the search space. And then you can compare distances based on the distance metric. Okay, and the action spaces can also be mapped into this search space as well. It can be macro actions or micro actions based on how long horizon it is. Okay, and in the end, you could have a graph space like this. Like this is your state space 0, 0, and then you go to here 0.9 minus 0.4. Of course, your state here, state is an abstraction of the original state space.
I think the trick here is all the words you haven't underlined. Right. So how do you map it? Which embedding? What's the metric? Right. So the conceptually, sure, but it's all of the stuff that's not on the slide that's the problem.
Yeah. How do we do the abstraction mapping?
Yeah,
yeah. So I would say yes, we can map it. The mapping may not be obvious, but I think that's why in life, like after a certain age, you stop to become better at like learning things, because perhaps maybe the embedding spaces or the abstraction spaces are kind of fixed already. So if it doesn't match with your existing set of abstraction spaces, you may not be able to solve the problem. Like okay, if, for example, for years, all right, there's this guy called John. The Game of Life.
Conway.
John Conway, yes.
Yeah.
So he also shares the John with me. Yep. So for years, he started this thing called knot theory. Then there was this knot that was unprovable. All right. And recently, I think 1-2 years back, some PhD students solved it. And using a totally different way of looking at the problem, nothing to do with knots at all. I think it became a picture solution or something like that. And this shows that, like, if let's say people have been working on this area for so long, and this is the abstraction space that they come up with, like say we need to use a number theory, you need to use this and that. But it could just be that the way to solve it is something else that is very different. And because we don't have this abstraction space in our heads, because like we don't think that way, Maybe a younger generation might be able to solve the problem by thinking in a different way. So we may not have the right expression spaces to solve the problem. Okay, and that's a fact. So not every problem can be solved because we may think that it's difficult to solve because we don't have the right tools to solve it. Like for example, if I want to use like I want to use algebra. Okay, I use algebra to solve predicting the next word. Okay, I mean, sure, you could try to use like next token prediction with probabilities and so on, or you could just, you know, do semantic space search. So if we can do semantic space search like what we are doing right now, actually it's also algebra. So let's use a different example. Let's talk about someone who is able to like play a certain video game, right? And this video game involves like it's a Pong game. Okay, requires you to bounce the ball off like that. So assume that like you are able to play this because like in real life you see the objects moving. Now I do a different kind of game. Instead of moving one straight line, the ball moves randomly like that. All right, but it's according to some other phenomenon that maybe someone in the future will have seen before. Like this is chaotic phenomena only present in the future. We cannot play this game very well, okay, because it's so chaotic to us. But to someone in the future, that chaos is structured. So with that kind of abstraction space, you are able to solve problems that like maybe the current generation might think that it's impossible to solve. But the younger generation might not have all this abstraction space biases. They might have new abstraction spaces. So again, I would like to just say that like, yes, finding the abstraction space is a difficult problem. But once you can find it in the right abstraction space, you can do like some form of graph traversal to solve the problem. Like this applies for math, this applies for knowledge, to plan from point A to point B and so on. Yeah. Okay, Kyren, you asked, as long as artificial intelligence, yes, traveling salesman problem, we might want to leave an unknown space for areas we cannot address yet. Okay, you're talking about abstraction space that is unlearned, right? So that you can learn a new one for a new environment. I think, yes, it's possible actually. There have been like cases whereby, you know, this thing called neuroplasticity. There's this neuroscientist called David Eagleman. He's a champion for this. I read all his books. So he has this live vest that basically there will be different vibrations at different parts of the vest that corresponds to like maybe different sounds. Or like you can put a camera on your head, it can correspond to the image. And what they found is that after a while, people learn how to recognize the vibrations and correlate to either the sound or the image. And this means that the skin vibration has formed a new kind of abstraction to match to something else. So maybe we grow new neurons to find new abstraction spaces, or we could plan with our existing abstraction spaces to try to match that. Yeah, so the brain is very flexible at pattern matching. So that could happen. So I don't have the answer. Do we grow new abstraction spaces? Don't know. Yeah. So yeah, maybe we do, maybe we don't. But the fact is that if we find the right abstraction space, maybe every intelligence problem can be mapped to like some form of maze traversal that you can just go from point A to point B. Any other comments on this slide? Okay, I think thanks so much for staying. I think I exceeded by like 1.5 hours or 1 hour. Yep. Just want to end off on this slide. So as you can see, this learning fast and slow, the idea is that you have both the neural network and you have the memory. Okay, memory enables fast learning. And if we can solve how we map things in memory, okay, how we choose the plans in memory will lead to this fast neural network being better. Okay, the intuition being better, gut feel being better. That's also why like chess masters or go masters, they can see the best move, like even without doing the look ahead sometimes. Okay, because they get better and better after their experiences. So the core problem to solve, okay, is memory, encoding, and retrieval. Once we can solve this, all right, and also like how to form the abstraction spaces is also part of it. Once we can solve this problem, we are like almost halfway there to fast and adaptable agents. It's a huge problem that is unsolved. Okay, right now retrieval augmented generation is like barely scratching the surface of what we can do with memory. It's only the input level memory. There's so many different memories that you can think about. like more of the different hierarchies, different kinds of modalities, and so on. Yeah. So I believe that even as we uncover all these advancements in AI, it will still be two systems. I mean, there could be more, but largely there will be a non-look-ahead system that is a neural network based, and a look-ahead system that is more like you need to care about the different transitions and so on. So this slow memory part with the transitions is very important. It will help to guide the fast network. And there's a lot of things that we can do that we just talked about, like how to encode emotions to select the transitions. To improve the fast transformer, we might do trajectories of past states and actions. That's the goal-directed decision transformer. We also have different abstraction spaces. We can form different modules of this fast and slow block in terms of hierarchy, sequential, abstracting the goal states by proximity and so on. And at an even more macro level, once we solve these few problems, we can do memory transfer between agents and so on. In fact, this problem here might be easier to solve actually. This is actually easier to solve than the abstraction space. Yeah. So my key focus right now is to continue work on like how to do the abstraction space because I think that's interesting. But actually right now, fast and slow can also do the multiple agents one. It's just that if we do it without solving this abstraction space, we can only do it for limited environments. I'm more interested in generic environments, and that's why I want to target the abstraction spaces first. Okay, this is a harder problem, and that will be the focus for the next few parts of my life. All right. So I do think this is more or less the roadmap that I'm thinking of for learning fast and slow. Overall, it's still going to be a fast neural network plus a memory retrieval part. How the different mechanisms change might differ, but eventually it's something like Daniel Kahneman's system 1 and system 2. System 1 is the rough kind of intuitive response. System 2 is the more deliberative, thoughtful response. And I think if we can build something like that, yeah, fast adaptable agents is definitely possible. Yeah. So I'll just end off on this slide. Any concluding comments before I end the session?
No, great job. Thank you.
All right. Thanks for coming and staying 1 hour more than I expected. But yeah. And well, we do chat some more. And yeah, hope to hear your comments as well. Okay. Bye, Ren.
Bye. Thank you.
You too.